In the vast expanse of our cosmic neighborhood, only 3 phenomena are known to traverse the stellar void between suns. Radiation streams across light years, cosmic dust drifts on interstellar winds. And apparently, whatever the heck 3i Atlas actually is, because on October 21st, 2025, alleged leaked footage from a Japanese space agency revealed this so-called comet looking less like your typical dirty snowball and more like a spacecraft with actual running lights. Now, let's be crystal clear. The legitimacy of this new footage is sketchier than a Bacali deal and hasn't been verified by any official source. But it absolutely sets off alarm bells about what this object might really be. Dr. Avi Loeb, the Harvard astrophysicist who's never been shy about thinking outside the box, noticed its trajectory enables what's called a solar Oberth maneuver, the kind of gravitational slingshot that only an advanced probe would use to efficiently accelerate. Then, in a twist that reads like a sci-fi thriller, amateur astronomer Tiago, better known online as Dobsonian Power, independently captured the same anomaly. Same coordinates, same shield bright front, and critically no cometary tail wear. There absolutely should be one. Now here's where things get downright suspicious. It's diving toward the sun during the 1 week when Earth's telescopes go completely blind from solar glare. Convenient timing for a natural object. Perfect timing for something else entirely. Stick around to the end, because the next few days might finally answer the oldest question humanity has ever asked. Are we alone in this universe? If these mysteries have your mind racing like they have mine, don't just lurk in the shadows. Hit that like button and subscribe right now to stay on the front lines as this story unfolds in real time. Drop a comment with where you're watching, from what time it is there, and whether you think the world is getting the full truth behind these earth-shattering discoveries. And if you want to amplify this hunt for hidden stories, share this video on X, Facebook, Reddit, or even in your private chats. Thank you for standing with us. You're the reason we chase stories no one else dares to follow. Part 1. The Japanese Likan. October 21st, 2025. Something materialized on the internet that shouldn't exist. The image showed an object near our sun that looked nothing like any comet we've ever documented. It looked engineered. You're staring at a clip that's been circulating through forums and social media channels for hours now. The quality is grainy, compressed, filtered through who knows how many hands before it reached your screen. But what it shows is unmistakable. There's an elongated form, metallic in appearance, hanging in the blackness near our start. Along its spine run bright nodes, evenly spaced, glowing with a white-blue intensity that makes your pattern recognition circuits scream artificial. There's no fuzzy halo around this thing, no diffuse cloud of gas and dust trailing behind it like every comet you've ever seen in a textbook. Just this sleek, symmetrical spindle suspended in space. The object in question is 3i Atlas, the third known interstellar visitor to breach our solar system. It was discovered on July 1st, 2025 by the Atlas Sevi, a network of telescopes designed to catch asteroids before they surprise us with an unannounced visit. For 3 months, astronomers tracked it as it fell sunward, analyzing its light, measuring its trajectory, cataloging its chemistry. Everything pointed to Comet. Unusual chemistry, sure, but still a comet. a frozen wanderer from another star system passing through ours on a one-way ticket to nowhere. Then this image leaked, and suddenly all bets are off. Look closely at what people are pointing out. The highlights along the body don't look random. They are placed, deliberate, like portholes on a submarine, or radiator panels on a spacecraft, or emitter arrays on something we don't have a name for yet. The glow is uniform, wrapping the object in a consistent, luminous sheath that reads more. Powered system, then ice ball reflecting sunlight. The symmetry is wrong for nature. Nature loves chaos. Nature makes potato-shaped rocks and lumpy snowballs. Nature does not make precision machine cylinders with evenly distributed light sources. The timing of this leak is critical. 3I Atlas is days away from perihelion's closest approach to the Sun, scheduled for around October 30th, 2025. It will pass within roughly 1.4 astronomical units of our star. That's about 130 million miles well outside Earth's orbit. No threat to us whatsoever. But here's the kicker. For about a week surrounding that closest approach, the comet will be nearly impossible to observe from Earth. Solar conjunction. The Sun will be directly between us and the object, flooding our telescopes with blinding light, making any detailed imaging essentially impossible. It's the perfect blackout window if you were going to do something near the Sun and didn't want. Earth-based telescopes watching, this is when you'd do it. The geometry hands you a natural curtain. The glare protects you, and that's exactly what makes this alleged leak so explosive. It surfaces right before the object vanishes behind the veil, showing us something that contradicts everything we think we know, then disappears before we can verify it. Now, let me be crystal clear about something. We are not claiming this image as authentic. We're treating it as an artifact, a catalyst, a thing that exists in the information ecosystem and has triggered a cascade of questions regardless of its provenance. The official scientific understanding remains that 3I Atlas is a natural object on a hyperbolic interstellar trajectory. It came from somewhere beyond our solar system. It's making a close pass by the Sun, and it will leave, never to return. The idea that it could be anything other than a comet would be world-shaking, civilization-altering, the kind of discovery that redefines what it means to be human in this universe. But if this image is real, that's exactly what we're looking at. The circumstances surrounding the observation make verification nearly impossible right now. The object is approaching the Sun from a geometry that places it at low apparent elongation from Earth's perspective. That means it's close to the Sun in the sky. Observing something that close to a blinding light source is technically challenging even for professional observatories. Solar glare washes out faint objects. Atmospheric seeing degrades near the horizon where the Sun sits. Heat shimmer from the ground distorts the view. It's the worst possible conditions for getting a clean, high-resolution image, which is of course exactly the right conditions for a leak narrative to thrive. When verification is hard, speculation runs wild. So where did this clip actually come from? That's what we need to figure out next. There's a watermark in the corner, UFO 5537. Anonymous posts claim it originated from a Japanese space agency or observatory. But there's no official statement, no press release, no matching data in public archives. Just this clip floating in the digital void, stamped with a code that means nothing to anyone outside whatever circle created it. And then there's another question altogether, one that ties the image to something even stranger. If this were a craft, if some intelligence from beyond our solar system sent a probe into our neighborhood, what would it be doing near the sun? Why risk the heat, the radiation, the sheer violence of that environment? Unless it's using the sun for something, unless it's preparing to execute a maneuver that human engineers have known about for decades but never built the technology to fully exploit. A solar Oberth maneuver, the biggest gravity assist in the solar system, the ultimate slingshot. We'll get to that. But first, we need to trace this image back to its source, or as close as we can get. We need to understand who's claiming what, why, and why provenance matters. We need to know what's missing from this picture that would let us call it real, because right now we're holding a photograph that could rewrite history, and we don't even know if it's genuine. 3I Atlas is out there, closing in on the sun. The blackout window is opening, and somewhere in the noise between verified science and unverified claims, the truth is waiting. Part 2. Provenance and credibility check of the leaked clip started showing up on X around mid-morning Eastern Time on October 21st, 2025. Users with varying degrees of credibility began sharing it, each adding their own layer of commentary, speculation, and alarm. The common thread in these posts was the claim that the footage originated from a Japanese source. Some said JAXA, Japan's space agency. Others mentioned university observatories or solar monitoring networks. But here's the problem. When you go looking for an official statement from any of these institutions, you find nothing. No press release, no data embargo announcement, no instrument logs matching the timestamp or field of view's silence. The watermark is the only consistent identifier, UFO 5537. It sits in the lower corner of every frame, a digital signature that tells us nothing about the actual origin. Watermarks can be added to anything by anyone. They don't authenticate content, they just mark it. And in this case, the marking feels deliberately cryptic, like it's designed to invoke mystery rather than provide accountability. If you were leaking classified data, would you stamp it with a code that screams unidentified flying object? Or would you strip metadata, anonymize the source, and distribute it through secure channels? The watermark feels performative. That doesn't mean the footage is fake, but it does mean we should be cautious. What's missing is everything that would let us verify this independently. Real astronomical data comes with headers. FITS files contain observation, metadata, instrument name, exposure time, filter selection, pointing coordinates, timestamp, with nanosecond precision, detector temperature, gain settings. If you hand an astronomer a raw frame from a professional observatory, they can trace it back to the exact telescope, the exact night, the exact sequence of observations. They can share whether the star field matches the claimed coordinates. They can compare the point spread function of stars in the frame to the known optical characteristics of that instrument. They can even verify whether the weather conditions and seeing quality that night would have allowed such an observation. None of that exists here. We have a processed, clip compressed, filtered, stripped of all the forensic details that would anchor it in reality. Which means we're left guessing. So why Japan specifically? There are a few plausible candidates if you're looking for high resolution, solar or near-solar imaging capability in that region. Japan operates several national observatories with advanced solar telescopes. Institutions like the National Astronomical Observatory of Japan have instruments capable of high-cadence solar monitoring. University networks across the country maintain smaller research-read telescopes. JAXA itself runs solar missions and maintains ground-based support infrastructure. Any of these could, in theory, have pointed at the right coordinates at the right time and captured something unusual. But none of them have come forward to claim it. And that's strange. If you're an institution with a world-first detection of something this significant, you don't stay silent. You publish, you hold a press conference, you coordinate with other observatories for confirmation. You don't let your data leak anonymously with a conspiracy-coded watermark. The alternative explanation is that this isn't institutional data at all. It could be from a private observatory, an amateur network, or even a foreign intelligence asset conducting independent monitoring. The problem with those scenarios is that they're harder to trace and even harder to verify. Private data doesn't have the same accountability structures. You can't FOIA request information from someone's backyard telescope. And if the source is genuinely sensitive, there's a reason they can't come forward, then we're stuck in limbo. We have evidence we can't authenticate. Then there's the question of whether the image itself is artificially generated. People have been poring over the frames looking for telltale signs of AI manipulation. Some point to the smooth gradients, the almost too perfect bokeh, the edges that look suspiciously clean for something imaged through Earth's atmosphere. AI-generated imagery has gotten frighteningly good in the past few years. Tools can fabricate convincing astronomical scenes, complete with realistic noise, star fields, and optical artifacts. If you wanted to hoax this, you could. But here's the counter-argument. Harsh solar-adjacent imaging through filters and heavy processing can also look artificial. Sensor blooming when a bright object saturates the detector creates halos that can seem unnatural. Compression algorithms smooth out detail in ways that mimic the look of synthetic imagery. Just because something looks too clean doesn't mean it's fake. It might just mean it's been processed aggressively to pull signal out of noise. The burden of proof, though, sits squarely on the shoulders of whoever is making the extraordinary claim. And right now, that claim is, this is an alien spacecraft. If you're asserting that you need more than a watermarked video clip, you need instrument metadata. You need raw data files. You need independent confirmation from multiple observers at different locations using different instruments. You need spectral analysis showing non-natural emission lines or thermal signatures inconsistent with cometary outgassing. You need trajectory data demonstrating non-gravitational acceleration that can't be explained by sublimating ice. Extraordinary claims require extraordinary evidence. We don't have that yet. The timing amplifies everything. 3I Atlas is about to slip behind the sun from Earth's perspective. We're entering the solar conjunction window, a period where observational geometry makes detailed imaging nearly impossible. This is exactly when false positives are most common. Low signal-to-noise conditions, high glare. Instruments pushed to their limits, trying to extract faint objects from bright backgrounds. Under those conditions, artifacts multiply. Diffraction spikes can look like structures. Internal reflections can mimic symmetry. Hot pixels can cluster in ways that suggest internality. Astronomers know this. They deal with it constantly. And they apply rigorous standards to separate real detections from instrumental ghosts. What do we have from official channels so far? Observations of 3I Atlas from Gemini, Hubble, the Very Large Telescope, and Keck have shown a cometary coma with unusual chemistry. Nothing metallic, nothing craft-like, just a fuzzy cloud of gas and dust surrounding a small, solid nucleus. The chemistry is weird, we'll get to that. But the morphology is Comet standard. There are jets, there's a faint tail, there's evidence of outgassing driven by solar heating. That's what you expect from a comet. It's not what you expect from a spacecraft. The media hasn't helped. Tabloid outlets have been running with headlines designed to maximize clicks, not clarity. Stories emphasizing the green glow of the comet, sensationalizing the nickel chemistry, hinting at metals without explaining the natural processes that produce them. We're not going to do that. We're going to keep the facts and the speculation in separate boxes so you can judge for yourself where the line is. So here's where we stand. The leaked image is unverified. It lacks the metadata and multi-source confirmation that would elevate it to evidence. It surfaced at a time and under conditions that make independent verification difficult. The aesthetic features that make it look artificial could also be consistent with heavily processed solar-adjacent imaging. We don't know who made it, where it came from, or whether it's genuine, but we also can't definitively prove it's fake. We're in the fog. What we do have, though, is something else. Another image, this one verified, traceable, posted by a known observer with a track record, an amateur. Astronomer with a solar telescope who pointed at the right coordinates at the right time and captured something that shouldn't be there if 3I Atlas were just an ordinary comet. That image gives the leak new oxygen. It doesn't prove the leak is real, but it keeps the door open. And that's what makes this story so hard to walk away from. Part 3. How the alleged leak differs from real comet imageries. Dive into what a comet actually looks like when you point a serious telescope at it. Real comets are messy. They're fuzzy, they don't have clean edges or symmetrical profiles. When you image a comet, what you're seeing is a small, solid nucleus, maybe a few miles across, surrounded by a diffuse cloud of gas and dust called the coma. That coma can stretch tens of thousands of miles in every direction. Behind the nucleus, solar radiation pressure pushes lightweight dust particles away from the sun, creating a tail that can stretch for millions of miles. Sometimes there's a second tail, a plasma tail made of ionized gas, glowing blue from fluorescence. These structures are shaped by solar, wind, radiation pressure, and the comet's own rotation. They're dynamic, asymmetric, constantly evolving. As the comet moves through space, 3I Atlas has been observed by some of the most powerful telescopes humanity has ever built. The James Webb Space Telescope pointed its infrared eyes at it. Hubble captured optical and ultraviolet spectra. The Very Large Telescope in Chile and the Keck Observatory in Hawaii both obtained high-resolution spectroscopy. All of these observations show the same basic picture. A comet, a fuzzy, diffuse object with a coma and evidence of outgassing. Nothing about those images suggests a solid, rigid structure. Nothing suggests metal. Nothing suggests machinery. But the chemistry is strange. That's worth emphasizing. Astronomers detected cyanide CN in the coma of 3I Atlas. Cyanide is common in comets. It's a molecule made of carbon and nitrogen, and it forms naturally in the cold, radiation-soaked environment of interstellar space. What's unusual is the presence of atomic nickel. Nickel vapor glowing in the coma at levels higher than you'd expect from a typical solar system comet. Even stranger, the iron lines that usually accompany nickel in vaporized rock are weak or absent entirely. It's like the comet is preferentially releasing nickel without iron, which doesn't make sense if you're just heating up generic rocky material. There's a natural explanation for this, and it involves some elegant chemistry. Under certain conditions, nickel can react with carbon monoxide to form nickel tetracarbonyl. That's a volatile compound, a gas that can form at relatively low temperatures compared to vaporizing pure metal. When sunlight hits nickel tetracarbonyl, it breaks apart, releasing nickel atoms into the coma, which then flows, emitting light at specific wavelengths that telescopes can detect. Iron doesn't form a similar carbon compound under these conditions, so you get nickel without iron. The process is unusual, but it's not impossible. It's just chemistry playing out in an environment we rarely get to observe up close. Spectroscopy from Keck and the Very Large Telescope has mapped the spatial distribution of CN and nickel around the nucleus. They show that these emissions are concentrated near the core and extend outward in patterns consistent with sublimation-driven jets. That's comet behavior. If this were a spacecraft venting propellant or leaking coolant, you'd expect different patterns. You'd expect collimated beams, repeating pulses tied to attitude control burns, or thermal signatures localized to specific emitter points. The spectroscopic data doesn't show that. It shows a nucleus shedding material as it heats up, exactly. Like a comet should know, here's where it gets interesting. There are reports of an antitail, a sunward jet. Most comet tails point away from the sun because radiation pressure pushes the dust outward. But some comets develop features that point toward the sun. These aren't true tails in the sense of material being blown backward. They're either jets of material erupting from the sunward face of the nucleus or perspective effects, where a curved dust trail appears to point the wrong direction when viewed from certain angles. Antitails are rare, but they're not unprecedented. And for 3I Atlas, the timing of this sunward feature coinciding with perihelion is noteworthy. It suggests active outgassing from the sun-facing hemisphere, which is exactly what you'd expect as the comet heats up. But let's compare that to what the leaked image shows. The leaked clip doesn't show a fuzzy coma. It shows a coherent, elongated object. The alleged lights along its spine don't look like diffuse gas emissions. They look like discrete sources, point-like, arranged with regularity. The overall appearance is rigid, structured, engineered. There's no tail, no envelope of dust, no asymmetric jets spraying off at random angles. Just this sleek form bathed in its own glow, hanging in space like it's parked there. That's not what comets look like. Even in extreme cases, when you image a comet in a specific filter that isolates one emission line, you still see diffuse structures. You see gradients, you see fuzzy boundaries. You don't see hard-edged objects with repeating geometric features. The visual language is completely different. Phase, angle, and filter choice can change appearance dramatically. If you observe a comet in a blue or green filter that isolates C and emission, you suppress the dust continuum and emphasize the gas. The object can look smaller, brighter, more concentrated. If you apply aggressive deconvolution algorithms to sharpen the image, you can introduce ringing artifacts that create the illusion of structure. If you over-sharpen or denoise too aggressively, natural features can start to look artificial. This is a known problem in image processing. You can make nature look engineered if you're not careful. But even accounting for all of that, the leaked image is hard to reconcile with the established morphology of 3I Atlas, NASA's official trajectory. Data confirms that the comet is not a threat to Earth. Its closest approach to us is about 1.8 astronomical units, roughly 168 million miles. That's nearly twice the distance from Earth to the Sun. If the leaked image makes the object look close, that's an illusion created by perspective, focal length, and framing. The comet is not nearby. It's not approaching Earth. It's falling to the Sun, and after perihelion, it will swing back out into interstellar space and never return. The geometry is locked in by observations spanning months. There's no ambiguity about where it's going. The question is what it is. Tabloid exaggerations have muddied the water. Headlines claiming the comet is turning green make it sound alien and toxic. In reality, the green glow is from CN, a normal cometary molecule. Claims that the comet is emitting alloys confuse spectroscopic detection of atomic nickel with metallurgy. These distortions feed into narratives that don't match the scientific record. We're going to stick to what's in the peer-reviewed papers and observatory reports. If the data changes, we'll update. But right now, the official story is unusual. Chemistry, yes. Craft-like morphology, no dot, except there's this image, and the image doesn't fit. It shows something that looks nothing like the cometary coma captured by Hubble or JWST or Keck. It shows something that looks designed. And that discrepancy is why this has become a lightning rod. That discrepancy is why people can't let it go. There's one more piece to this puzzle. A maneuver. An orbital trick that could explain why any intelligence would send a probe to skim past the Sun at this exact moment. It's called the Oberth effect. And if you understand it, you understand why the timing of the conjunction window matters so much. Because if you're going to accelerate out of the solar system at maximum efficiency, there's only one place to fire your engines. And that's right where 3I Atlas is going to be in 9 days. Part 4. The Tiago Dobsonian Power Solar Scope Capture, October 20th, 2025. An amateur astronomer named Tiago posted a raw frame from his solar telescope. He goes by Dobsonian Power online, a handle that reflects his enthusiasm for large aperture, manually operated telescopes typically used for deep sky observing. But Tiago also maintains solar imaging equipment. And on that morning, he pointed his scope at a specific set of coordinates provided by NASA's ephemeris data for 3I Atlas. He captured something. The image shows a compact, bright region against the diffuse glow of the solar corona. There's a pronounced forward-facing structure, a shield, as some observers have called it, angled toward the sun. Behind this bright front section is a faint, conical puff of material, asymmetric and less luminous than the leading edge. Critically, there's no extended tail, no long streamer of dust stretching away from the sun, just this concentrated, front-heavy form with a short, diffuse wake. This is verified data in the sense that Tiago is a known observer with a public track record. His post includes time-stamped coordinates and equipment details. Other amateur astronomers have cross-referenced his pointing solutioned with JPL's ephemeris and confirmed that he was indeed looking at the right location at the right time. This isn't an anonymous leak. This is traceable, community verification. It's not agency certified, peer-reviewed science data, but it's not nothing either. It's a data point. The raw frame is speckled with colored noise, hot pixels, cold pixels, sensor artifacts amplified by high gain and aggressive solar filtration. This is completely normal for solar-adjacent imaging. When you're trying to capture a faint object near the sun, you're pushing your detector to its limits. You crank the exposure time as long as you can without saturating on the solar disk. You crank the gain to pull signal out of the background. And when you do that, all the imperfections in your sensor light up. The result is a grainy, noisy frame that requires careful processing to extract meaningful signal. Tiago posted the raw data, which is exactly what you want to see. Raw means unmanipulated. Raw means you can evaluate the noise characteristics yourself and judge whether what you're seeing is real structure or artifact. What this frame does is confirm that something is there at the predicted coordinates, at the predicted time, with a morphology that matches neither a typical cometary coma nor the appearance of a background star or galaxy. The front brightening is significant. Most comets brighten uniformly or show jets erupting from the nucleus in multiple directions. A strongly asymmetric, forward-facing bright region is unusual. It could be a sunward jet material erupting from the hemisphere facing the sun as that surface heats up. That would be consistent with the anti-terror reports from spectroscopic observations. The sun-facing side is active, venting gas and dust directly toward the star, creating a compact, bright feature that doesn't have time to disperse before the observer's line of sight cuts through it. Or it could be something else. Forward scattering. When sunlight hits small particles, it scatters in all directions. But there's a preferential scattering angle that enhances brightness when you're looking at the object from a specific geometry. If 3i Atlas has a dust cloud concentrated on its sunward side, and Tiago's viewing angle happened to align with that scattering sweet spot, you'd see exactly this kind of bright leading edge. It's an optical effect, not a physical structure. The brightness isn't intrinsic to the object. It's a consequence of how sunlight interacts with dust particles at that particular phase angle. This effect is well understood in planetary science. It's why the moon looks brighter at full phase than at crescents. It's why Saturn's rings brighten dramatically when Earth crosses the ring plane. Physics, not propulsion. But then there's the cone, the faint, diffuse structure trailing the bright front region. If this were purely forward scattering, you'd expect the brightness to fall off smoothly with distance from the nucleus. Instead, there's a defined, conical shape, like a jet or plume, that suggests directed outgassing. Material flowing away from the nucleus in a preferential direction, possibly along the object's rotation axis or from a localized active region. Comets do this all the time. They develop jets that create asymmetric chemae and odd tail structures. What's striking here is the lack of an extended tail. At the distance 3i Atlas is from the Sun. Right now, you'd expect solar radiation pressure to have pushed dust particles into a noticeable tail. The fact that Tiago's image doesn't show one either means the dust production is lower than expected, or the particle size distribution is skewed toward larger grains that don't get pushed as easily, or something about the viewing geometry is hiding the tail. Or, if we're entertaining the alternative hypothesis, there is no tail because this isn't a comet shedding dust. It's a craft, venting something for thermal management or propulsion. And whatever it's venting doesn't behave like cometary dust. The chemistry data supports unusual activity on the sunward side. The detection of CN and nickel in the coma, combined with the spatial distribution showing concentration near the nucleus, aligns with the idea that the sun-facing hemisphere is actively sublimating volatiles. The carbonyl chemistry pathway we discussed earlier could be operating at peak efficiency on that side, liberating nickel atoms as the surface heats up. This could produce a localized, bright region without requiring any artificial processes. It's weird, but it's plausibly natural. Tiago's image has to be evaluated for artifacts. Solar telescopes deal with conditions atmospheric turbulence, thermal ripples that can distort structure. The sun heats the ground, creating convection cells in the air above the telescope. Those cells act like moving lenses, bending light and blurring images. High-cadence imaging and lucky imaging techniques can mitigate this, but the artifacts don't disappear completely. You can get false structures, you can get apparent symmetries that aren't real. The fact that multiple observers, including whoever produced the leaked clip, are reporting similar morphology helps rule out a single frame glitch. If only one person saw this, you dismiss it as artifact. When multiple independent sources report consistent features, it becomes harder to ignore. What this frame does not do is prove that 3i Atlas is artificial. It proves that something anomalous in appearance is present at those coordinates. It confirms that the object's morphology is unusual enough to warrant closer scrutiny. It validates that the leaked clip, whatever its provenance, is at least describing an object that exists in that location. It doesn't tell us what the object is, it just tells us it's there, and it looks strange. NASA's distance and trajectory data remain. The anchor, the object, is not approaching Earth. It is not on a collision course. The narrative around 3i Atlas is not about impact risk. It's about the possibility, however remote, that we're observing something that doesn't fit the standard model of cometary behavior. The fact that this is happening right as the object approaches the optimal location for a high energy maneuver is what gives the speculation its teeth. If you wanted to accelerate a spacecraft using the sun's gravity, well, you'd do it at perihelion. You'd fire your engines at the lowest point in your orbit, when you're moving fastest and the gravity gradient is steepest. Every bit of delta V you add at that moment gets multiplied by the depth of the well. It's called the Oberth effect, and it's one of the most efficient tricks in orbital mechanics. And 3I Atlas is going to pass through that exact sweet spot in 9 days, while Earth-based telescopes are blind. Part 5. Why the Oberth maneuver keeps coming up. The Oberth effect isn't some sci-fi fantasy cooked up by Hollywood screenwriters. It's hard science. Basic orbital mechanics that any spacecraft designer learns in their first semester. The principle is deceptively simple. If you want to change your energy in orbit, you do it where you're moving fastest. When you fire a rocket engine, the energy you add to your spacecraft depends not just on the thrust of the engine, but on your velocity. At the moment you fire it, the faster you're going, the more kinetic energy each unit of propellant adds to your total energy budget. It's counterintuitive, but it's mathematically solid. Firing at the bottom of a gravity well where your orbital velocity is highest gives you more bang for your buck than firing in deep space, where you're moving slowly. Human missions have been using this trick for decades. The Voyager probes swung past Jupiter and Saturn, using gravity assists to steal momentum from the planets and fling themselves toward interstellar space. The Cassini mission used multiple planetary flybys to reshape its trajectory and insert into Saturn orbit. The Galileo probe used Venus and Earth flybys to gain enough energy to reach Jupiter. Every deep space mission that needs a big velocity change thinks about the Oberth effect. It's how you get anywhere in the solar system without carrying impossibly large fuel loads. Now apply that logic to an interstellar probe. If you're an intelligence from another star system and you want to send a reconnaissance craft through our solar system, you would design its trajectory to maximize science return and maneuverability. You'd want to pass close to multiple planets to observe them. You'd want to sample the local environment, check for biosignatures, map gravitational anomalies, measure the star's magnetic field and radiation output, and when you're done, you'd want to leave fast either to return home, continue to the next star, or settle into an orbit where you can loiter and watch. To do any of that efficiently, you'd use the sun. Dr. Avi Loeb, the Harvard astrophysicist we mentioned earlier, has been pointing this out publicly since 3I Atlas was discovered. He's noted a series of anomalies in the object's trajectory and properties that, when taken together, suggest the possibility of deliberate design. First, the trajectory itself. The first atlas approached the solar system from a direction close to the ecliptic plane within about 5 degrees. The ecliptic is where all the planets orbit. It's the busy highway of the solar system. If you're trying to visit planets, you'd aim for that plane. A random interstellar object has no reason to prefer the ecliptic. The galaxy is three-dimensional. Interstellar space is isotropic, an object on a purely ballistic, gravitonially trajectory from another star system should arrive from a random direction in the sky. The fact that 3I Atlas came in near the ecliptic is unusual. Second, the close planetary encounters. 3I Atlas's trajectory brought it within tens of millions of miles of Venus, Mars, and Jupiter. Not collisions, but close approaches by interstellar standards. If you wanted to fly by multiple planets on a single pass through the system, you'd design exactly this kind of trajectory. It's efficient, it's opportunistic. It's what a mission planner would do. Third, the mass estimate. Loeb points out that 3I Atlas appears to be more massive than the first two interstellar visitors, 1I Oumuamua and 2I Borisov. Mass estimates for comets are model-dependent and uncertain. So this point is debatable, but the claim is that 3I Atlas is carrying more material than you'd expect for an object of its size and activity level. If it's a spacecraft with propellant tanks and structure, that would explain the discrepancy. Fourth, the chemistry of the nickel-over-iron ratio and the low water fraction detected by JWST at large heliocentric distances. Water ice is the dominant, volatile in most solar system comets. The fact that 3I Atlas is carbon dioxide rich and water poor is unusual, though not impossible. Interstellar comets could form in environments with different temperature profiles and chemical compositions than our local comets. But it's one more thing that doesn't fit the template. Fifth, the sunward Jetha anti-tail feature. If this is purely natural outgassing, it's happening at a specific location on the nucleus and pointing in a specific direction. That's possible, but it's convenient. It's exactly what you'd see if the object were firing a thruster to adjust its trajectory. Sixth, the timing. 3I Atlas will reach perihelion at a moment when Earth-based telescopes cannot observe it closely. Solar conjunction, the Sun is in the way. This provides a natural cover for any maneuvering. If the object were to fire its engines during this window, the only way we'd detect it is from spacecraft at different locations in the solar system, SOHO, stereo, maybe some planetary orbiters. But those instruments aren't designed for high resolution imaging of faint objects. They are designed for solar physics and wide field surveys. The chances of catching a brief thruster burn are low. By the time 3I Atlas emerges from conjunction and Earth-based telescopes can see it again, the burn would be over. All we'd have is the post-maneuver trajectory, and we'd have to infer the delta V from the difference between the predicted orbit and the observed orbit. And that's the test. That's how we'll know if 3I Atlas's post-perihelion trajectory matches. The gravity-only predictions, the Oberth hypothesis weakens. If there are systematic residuals, if the object ends up in a slightly different orbit than expected, the hypothesis strengthens. Orbital mechanics is precise. You can predict where an object will be months or years in advance based on its current trajectory and the gravitational forces acting on it. Any deviation from that prediction means a force we didn't account for. Outgassing can produce small deviations. Comets do this. The asymmetric venting of gas creates a rocket effect that nudges the comet's orbit. But those nudges are typically small and random. If 3I Atlas shows a large, systematic change in its trajectory, something that looks planned, that's when the conversation shifts from interest in Comet to we need to talk. NASA says the object is not a threat. Its trajectory keeps it far from Earth. The perihelion distance is 1.4 astronomical units. Well, inside Earth's orbit, but with no intersection. After perihelion, it will swing back out and leave the solar system on its hyperbolic escape trajectory. The Oberth speculation isn't about collision risk. It's about the possibility that what we're tracking isn't following a purely ballistic path. It's about the possibility that something is steering. There are two branches to this speculation, and they lead to very different outcomes. The first branch is acceleration. If 3I Atlas fires its engines at perihelion to add velocity, it could boost itself onto a faster escape trajectory. Maybe it's done with this solar system and wants to head to the next star on a tighter timeline. Maybe it's returning home with data. Maybe it's racing ahead to prepare for something else. An Oberth burn to accelerate out would be the most fuel-efficient way to leave. You'd light your engines right at perihelion when you're already moving. At maximum velocity relative to the sun, every kilogram of propellant you burn adds maximum energy to your total budget. You leave faster, farther, with less fuel costs than any other maneuver. The second branch is deceleration. This one is more unsettling. If the object fires its engines retrograde against its direction of travel, it can shed velocity, bleed off speed. Instead of escaping the solar system, it could drop into a bound orbit. It could stay here, loiter in the inner system, continue observations, deploy secondary payloads, establish infrastructure. A deceleration burn at perihelion is still efficient because you're burning at high velocity, but the outcome is opposite. Instead of leaving, you're capturing yourself into orbit. You're setting up shop. Both scenarios are speculative. Both require evidence we don't have yet. But both are consistent with the Oberth maneuver as a propulsion strategy, and both explain why the conjunction window matters so much. If you're going to burn your engines, you do it when nobody can see you. You do it when the sun's glare hides your plume. You do it when Earth's telescopes are blind and the only witnesses are spacecraft that aren't looking for you. Now, connect this back to the leaked image. If the evenly spaced bright nodes along the object's spine are real, what could they be? One interpretation is thruster banks clusters of engines arranged along a spinal truss designed to provide thrust vectoring and attitude control. Another interpretation is radiator panels. Any propulsion system generates heat. If you're doing a high-energy burn near the sun, you need to dump that heat or your systems cook. Radiators glow. They emit in the infrared and sometimes visible wavelengths if they're hot enough. A spacecraft with an active thermal management system could produce exactly the kind of evenly spaced bright nodes people are seeing in the image. Or they could be sensor artifacts, diffraction spikes, internal reflections in the optical path. CCD bloom from a bright, compact nucleus, hot pixels clustering in a pattern that looks deliberate but isn't. The key is the post-perihelion data. When 3I Atlas emerges from conjunction in early November, observers worldwide will be pointing every available telescope at it. Part 6. Morphology, anomaly rod-like body. With lights, the human brain is an exquisite pattern recognition machine. It evolved to spot predators in the underbrush, to see faces in the shadows, to detect order in chaos, because order often meant intention, and intention often meant danger or opportunity. This is why we see animals in clouds and faces in rock formations and apparently spacecraft in cometary images. We're wired to interpret ambiguous visual data as meaningful structure. The question is whether what we're seeing in these images of 3I Atlas is pattern or pareidolia. Is there really something there that doesn't fit natural expectations? Or are we doing what we always do, seeing what we want to see? Let's break down the visual claims in detail. The alleged leaked image shows an elongated, spindle-shaped object. The aspect ratio is high and significantly exceeds width. It's not a sphere, it's not an irregular potato shape. It's a rod. Along the central axis of this rod are discrete, bright points, not a continuous glow, not random scattering, but discrete nodes, evenly spaced, each with similar brightness and color. The spacing looks deliberate, geometric. If you drew lines connecting them, you'd get a straight spine with regular intervals. That's the first red flag for the human visual system. Regular spacing in nature is rare. Crystals do it. Molecular structures do it at microscopic scales, but macroscopic objects, especially ones made of ice and rock dome, tend to self-organize into evenly spaced glowing dots. Then there's the shahitha, blue-white glow wrapping the entire object, creating a halo effect that enhances the sense of symmetry. It's uniform. The brightness doesn't vary much from one end to the other. There's no obvious nucleus, no single bright core that you'd expect from a comet with a solid, reflective surface surrounded by diffuse gas. Just this smooth, distributed luminosity that makes the whole structure look like it's illuminated from within, or like it's emitting light rather than reflecting it. If you were designing a spacecraft for interstellar travel, what would it look like? The answer depends on your engineering constraints. Speed is one constraint. If you're moving at a significant fraction of light speed, you need shielding up front to absorb impacts from interstellar dust and gas. A Whipple shield named after astronomer Fred Whipple's a multi-layer bumper system designed to vaporize incoming particles before they hit critical systems. You'd place this at the bow, the leading edge, oriented in your direction of travel. That would create a bright, reflective or ablative surface facing forward. If sunlight hits that surface at the right angle, it glows. It stands out behind the shield. You'd have a spinal, truss load-bearing structure running the length of the craft, connecting propulsion at one end to payload and sensors at the other. Along this truss, you'd mount systems, fuel tanks, power generators, radiators, communication arrays, maneuvering thrusters. Each of these systems has its own thermal signature. Radiators in particular need to be distributed along the structure to efficiently dump heat. If your power system is running hot, if you're doing a high-energy maneuver, those radiators glow. They emit primarily in the infrared, but if they're hot enough, they can emit visible light. A spacecraft with an active thermal management system, viewed from a distance, could look exactly like a rod with evenly spaced, glowing nodes. Maneuvering jets are another possibility. If you're doing fine attitude control, keeping your orientation stable or adjusting your spin rate, you'd use small thrusters arranged around the vehicle's center of mass. Fire them in sequence, and they create a pattern of bright flashes. If someone captures a long exposure image while you're actively maneuvering, those flashes integrate into bright spots. Spacing depends on your thruster layout, but symmetry is desirable for balance. Engineers like symmetry. It simplifies control algorithms. So you'd place thrusters at regular intervals, and that's what an observer would see. But let's consider the natural alternative. Could a comet produce this appearance without being artificial? Start with the geometry. Comets are not usually elongated rods, but they can be. One-eye Oumuamua was estimated to have an aspect ratio of 10:1, a cigar-shaped, tumbling rock. If Three-Eye Atlas is similarly elongated, and if we're viewing it nearly along its long axis, end in it could appear as a narrow spindle. The question is whether that's consistent with the observed rotational light curve and the spectroscopic data, which suggests a more typical cometary shape. Next, the bright nodes. Could these be jets seen end-on? Comets develop active regions? On their surfaces, where sunlight sublimates ice and drives gas and dust into space, if Three-Eye Atlas has multiple jets erupting from along its rotation axis, and if we're viewing those jets head-on, each jet could appear as a bright spot. The spacing would depend on where the active regions are located, which is controlled by surface geology and rotation states. Random in principle, but possibly clustered if there's some underlying structural pattern in the nucleus, like fracture lines or compositional boundaries. It's not impossible. It's just unlikely to produce the kind of regularity people are reporting. Forward scattering is another mechanism. When sunlight hits small dust particles, it scatters preferentially in the forward direction. If Three-Eye Atlas has a dusty coma concentrated around the nucleus, and if the viewing geometry aligns with a forward scattering angle, the whole coma lights up. But forward scattering tends to produce a smooth, diffused glow, not discrete points. 2. Get point-like features, you'd need clumps of dust concentrations separated by voids. That could happen if the comet's outgassing is episodic, puffing out material in bursts rather than continuously. Each puff creates a denser region, and those regions scatter light more efficiently. Seen from a distance, they could look like nodes, but the spacing would be irregular, changing as the puffs expand and disperse. The fact that multiple images show consistent node positions argues against this, unless the puffs are being replenished at the same locations, which brings us back to fixed active regions and makes the natural explanation more contrived. Deconvolution. Artifacts are a real concern. When you process astronomical images to sharpen detail, you're mathematically inverting the point spread function of your telescope. This amplifies real structures, but also amplifies noise. If you're not careful, you can create false structures around bright sources, phantom edges, repeating patterns tied to the symmetry of your PSF. Professional astronomers apply deconvolution cautiously and validate the results against raw data. If the leaked image has been heavily processed, if someone pushed the sharpening too far, the nodes could be artifacts. But the raw Tiago frame also shows front brightening, and it's not heavily processed, so either multiple independent processing pipelines are producing similar artifacts, which is suspicious, or there's real structure there. The chemistry of Three-Eye Atlas adds another layer. The nickel cyanide anomaly. Carbonyl chemistry can explain atomic nickel without iron, but it's unusual. It requires specific temperature and pressure conditions. The fact that this chemistry is happening at all suggests active volatile processing. Near the nucleus, nickel tetracarbonyl forms at relatively low temperatures. When nickel-bearing minerals interact with carbon monoxide, sunlight breaks it apart, releasing nickel atoms. Those atoms fluoresce, emitting at specific wavelengths. If the nickel emission is concentrated in specific regions, either because the active areas have more nickel-rich material or because the temperature distribution is uneven. You could get bright spots in nickel-filtered images. That's a natural process. But it's also exactly what you'd see if a spacecraft were venting something nickel-rich as part of its thermal or propulsion system. Filter choice matters enormously. If you image 3I Atlas in a filter that isolates CN emission, you're seeing only the gas, not the dust. The coma collapses visually, becoming smaller and brighter. Active regions stand out. If you image in infrared, you're seeing thermal emission from warm dust. The appearance changes completely. If you image in visible light with no filter, you're seeing reflected sunlight from the nucleus and dust plus gas fluorescence. The object looks fuzzy and diffuse. The leaked image appears to be in blue or white light, emphasizing the symmetry and smoothness of the sheath. The Tiago frame is likely filtered for solar observation, suppressing certain wavelengths to avoid sensor saturation. Each filter tells a different story. The trick is figuring out which story is true. Phase angle also plays a role. The angle between the sun, the object, and the observer. At certain phase angles, small particles exhibit opposition surge, a sudden increase in brightness when sunlight backscatters directly toward the observer. This can make a dusty coma look artificially bright and create the illusion of a shiny metal surface. Conversely, at other phase angles, the same particles look dark. If 3I Atlas is at a phase angle where forward scattering or opposition surge is strong, natural materials can mimic reflective metal. This is well documented in planetary science. Icy moons, dusty rings, even the lunar regolith all show phase-dependent brightness effects that can be mistaken for intrinsic material properties. Part 7. Timing and Trajectory Oddities. Let's talk about where 3I Atlas came from and why that matters. Interstellar space is big, interstellarly big. The nearest star system to our Sun, Alpha Centauri, is 4.3 light-years away. That's 25 trillion miles. If you picked a random direction in the sky and threw a rock, the odds of it hitting our solar system are effectively zero. Space is mostly empty. Stars are tiny targets separated by oceans of nothing. For an object to arrive at our Sun from interstellar space, it has to be aimed. Either it's aimed by gravity perturbed by the galactic potential and stellar encounters over millions of years until it happens to intersect our system, or it's aimed intentionally, launched on a trajectory designed to reach us. Random interstellar objects arrive from random directions. The galaxy is three-dimensional. There's no preferred orientation. The plane of the Milky Way is flat on galactic scales, but on the scale of individual star systems, there's no reason an incoming object should align with anything in particular. It should come from above or below the ecliptic, as easily as from within it. The ecliptic, remember, is the plane in which Earth and the other planets orbit the Sun. It's defined by the angular momentum of the solar nebula that formed the planets 4.6 billion years ago. It's our plane, it's parochial to our system. An interstellar visitor has no business caring about it. And yet, the first Atlas approached from a direction within about 5 degrees of the ecliptic. Avi Loeb has pointed this out repeatedly. 5 degrees is close. Not exact, but close enough that if you were planning a tour of the solar system's planets, you'd aim for that geometry. The planets all orbit within a few degrees of the ecliptic. If your goal is to fly by multiple planets on a single pass through the system, you'd inject into a trajectory that crosses the ecliptic plane at a shallow angle. That way, you maximize your chances of encountering planets without needing large course corrections. It's Mission Design 101, efficient, opportunistic. Exactly what you do if you had limited propellant and wanted to see as much as possible. Point 3, I-Atlas's trajectory brought it close to Venus, Mars, and Jupiter. Not collision close, but within tenths of millions of miles for Venus and Mars. That's a close encounter by interstellar standards. For Jupiter, it's a distant pass, but still within the gravitational influence of the planet. If you're a reconnaissance probe, these are prime targets. Venus to study runaway greenhouse atmospheres, Mars to check for extinct or extinct life, Jupiter to sample the magnetosphere and observe the Galilean moons. You'd want to pass near all of them, and 3 I-Atlas's trajectory does exactly that. Now, you might argue that this is selection bias. We only notice interstellar objects that come close to the Sun because those are the ones we can detect. Objects that pass through the outer solar system without approaching the inner regions stayed too faint for our surveys. So maybe there are hundreds of interstellar visitors every year, and we only see the ones that happen to come close enough and at the right geometry to be discovered. That's a valid point. Our detection efficiency is biased toward objects that approach the Sun and brighten from solar heating. But even accounting for that bias, the ecliptic alignment is unusual. There's a broad range of possible trajectories that would bring an object close to the Sun, and most of them don't align with the ecliptic. The fact that 3 I-Atlas does is a statistical outlier. Not impossible, just unlikely. The perihelion distance and timing add to the oddity. Perihelion occurs around October 29th or 30th, 2025, at a distance of approximately 1.36 to 1.4 astronomical units from the Sun. That's inside Earth's orbit, but outside Venus's orbit. It's a sweet spot close enough to the Sun for significant solar heating, which would activate any icy volatiles and make a comet brighten dramatically, but not so close that the object risks structural damage from thermal stress. If you're trying to do a high-energy maneuver, you want to get as close to the Sun as you can without cooking your spacecraft. 1.4 astronomical units is reasonable for that. It's hot, but manageable with proper heat shielding. The closest approach to Earth is about 1.8 astronomical units, roughly 168 million miles. That's farther than the Sun, so there's no danger of collision or even a close pass. The geometry places Earth off to the side, while 3 I-Atlas dives toward the Sun. But from Earth's perspective, the object and the Sun are nearly aligned in the sky during perihelion. That's solar conjunction. The Sun's glare overwhelms any feint. Objecting by, it's the same reason we can't observe Mercury and Venus when they pass behind the Sun from our vantage point. The Sun is too bright. The contrast is too high. Our telescopes and cameras can't separate the faint object from the overwhelming foreground. Solar conjunction happens routinely in spaceflight operations. When a Mars or Jupiter-bound spacecraft passes behind the Sun, as seen from Earth, we lose communication for days or weeks. NASA's Deep Space Network can't maintain a radio link because the sun's radio emission drowns out the spacecraft's signal, and solar plasma distorts the transmission. Mission planners design around these blackout windows. They upload, command, sequences in advance, put the spacecraft into safe mode, and wait for conjunction to end before resuming operations. It's a known operational constraint, and it's the perfect cover for any maneuver you don't want observed. If 3i Atlas were a spacecraft, and if it intended to perform an Oberth burn at perihelion, the conjunction window provides natural operational security. Earth-based telescopes can't see you. Earth-based radar can't track you. Radio observatories can't detect emissions because the sun's radio output is overwhelming at those frequencies. You're hidden, not invisible to spacecraft at other locations in the solar system. SOHO, stereo. Maybe some planetary orbiters could catch glimpses depending on their geometry. But those platforms aren't optimized for high-resolution imaging of fast-moving, faint objects. Their primary missions are solar observation or planetary science, not tracking comets. The odds of catching a transient thruster burn are low unless someone is specifically looking for it. Then there's the sunward and detail. Multiple spectroscopic observations have reported a jet or extension of the coma pointing toward the sun. Antitails are rare in comets. Normally, radiation pressure pushes dust away from the sun, creating tails that point in the antisolar direction. A sunward feature suggests either active outgassing from the sun-facing hemisphere, which is plausible, given that's the side receiving the most heating, or a perspective effect, where a curved dust trail appears to point the wrong direction when viewed from certain angles, but perspective effects are usually transient. They change as the observer's geometry changes. If the sunward feature persists across multiple observations from different dates and viewing angles, it's more likely a real physical structure. Jet of material flowing out from the nucleus toward the sun. Why would a comet do that? Sublimation-driven jets usually follow the local temperature gradient. The hottest parts of the nucleus vent the most material. On the day side, the sun-facing hemisphere, you'd expect strong outgassing. If that outgassing is concentrated in a jet rather than distributed evenly, and if the jet happens to point along the sun-comet line, you'd get a sunward extension. It's not common, but it's not impossible. The alternative interpretation is that the object is firing a thruster specifically, a forward-facing thruster designed to slow it down. If you're doing a retrograde burn to shed velocity and capture into a bound orbit, your engine exhaust would point forward along your direction of travel. And depending on your orientation, that exhaust could be directed sunward. Either explanation is consistent with the observations. The question is, which one is more likely? The mass estimate is contentious. Loeb claims 3i Atlas is more massive than 1i Oumuamua or 2i Borisov. Mass estimates for comets are derived from brightness, assumed albedo, and dynamical behavior. All of these are model dependent. If you assume the object is a porous ice-dust mix with typical cometary albedo, you get one mass. If you assume it's denser, more compact with high albedo, you get a different mass. If you include structure like internal tanks or machinery, the mass goes up. The uncertainty is large. But if the object is genuinely more massive than expected for its size and activity level, That's another data point that doesn't quite fit the standard Comet model. After perihelion, the test becomes clear. Observers will track 3I Atlas's position. As it moves away from the Sun, they'll compare the observed trajectory to the predictions based on gravity alone. Orbital mechanics is deterministic. If you know an object's position, velocity, and the gravitational forces acting on it, you can predict its future trajectory with high accuracy. Any deviation from that prediction indicates an unmodeled force. For comets, that force is usually outgassing. The asymmetric venting of gas creates a small rocket effect. It's random, noisy, and typically small. If 3I Atlas shows a systematic deviation, a change in velocity that's larger than expected from outgassing, and points in a specific direction, that's evidence of something else. If the deviation is consistent with an Oberth burnover accelerating out or decelerating into a bound orbit, the hypothesis gains teeth. Part 8. Cover-up hypothesis. Why would data be withheld? Let's start with the boring reasons, the ones that don't involve shadowy government agencies or interstellar diplomacy. The reasons why scientific data might not be immediately available to the public even when something interesting is happening. First, data quality. Not every observation is good enough to publish. Astronomical images can be degraded by poor seeing, clouds, equipment malfunction, calibration errors, or just bad luck. If you point a telescope at 3I Atlas and the atmosphere is turbulent, your image will be blurry. If the object is too faint, your signal-to-noise ratio will be terrible. If you miscalculate the pointing coordinates, you'll image the wrong patch of sky. Professional astronomers deal with this constantly. They take multiple exposures, throw out the bad ones, and only publish the good ones. If an observatory captures something ambiguous, something that looks interesting but isn't scientifically rigorous, they might hold it back until they can confirm it with better data. That's not a cover-up. That's quality control. Second, calibration. Raw telescope data is messy. It includes instrumental artifacts, dark current, bias frames, flat field variations, hot pixels, cosmic ray hits. Before you can analyze the science target, you have to subtract all that noise. Calibration can take days or weeks, depending on the complexity of the instrument and the expertise of the team. If someone captured 3I Atlas during perihelion, but they're still working through the calibration pipeline, the data won't be public yet. Patience is required. Science doesn't happen in real time. Third, proprietary periods. Many observatories grant the observers who requested the telescope time a proprietary period during which they have exclusive access to the data. This gives them time to analyze the results, write a paper, and submit it to a journal before anyone else can scoop them. Proprietary periods can last months or even a year. It's a standard practice designed to reward the effort of writing a successful observing proposal. If someone has proprietary data on 3I Atlas, they're not obligated to release it immediately. Eventually, the data becomes public, but not right away. Fourth, spacecraft safety. If the relevant data comes from a space-based observatory like JWST or Hubble, the operations teams prioritize the health of the spacecraft over any individual science target. During solar conjunction, some spacecraft go into safe mode to protect their instruments from solar heating or to avoid risky pointing geometry. If imaging 3I Atlas during perihelion would require pointing too close to the sun, the observatory won't do it. The risk of damaging expensive hardware outweighs the science return, so the data you want might simply not exist because the observation was deemed too risky. Those are the benign reasons. They're mundane. They're how science actually works. They don't make for exciting narratives, but they're statistically the most likely explanation for why here resolution. Imagery of 3I Atlas at perihelion isn't flooding the internet right now. Now, let's consider the less benign possibilities, the scenarios where information is withheld not because of technical or procedural reasons, but because someone decided it shouldn't be public national security. If 3I Atlas were determined to be artificial, that information would have strategic implications. It would confirm that interstellar travel is possible and that someone achieved it. It would raise questions about intent. Is this passive or active? Is it observing us or interacting with us? Is it alone or part of a larger fleet? These questions have defense implications. Governments might decide that public disclosure should be delayed until there's a clearer understanding of what's happening and what the appropriate response should be. That's not necessarily nefarious. It's risk management. In the absence of complete information, caution is rational. Fear of panic. The history of public reactions to astronomical discoveries is mixed. When Halley's Comet passed through Earth's orbit in 1910, tabloids claimed the comet's tail contained poisonous gases that would kill everyone. People panicked. Some sealed their homes. Some bought gas masks. None of it was justified. The tail was so diffuse it had no effect on Earth, but the panic was real. If 3I Atlas were announced as a potential artificial object without conclusive evidence, the same kind of hysteria could erupt. Governments and institutions might decide that avoiding panic justifies temporary withholding of ambiguous data. Again, not necessarily a cover-up in the sinister sense, just a judgment call about public communication. Confirmation before disclosure. Imagine you're an astronomer who captured an image of 3I Atlas that looks artificial. You're excited. You're also terrified of being wrong. If you release it and it turns out to be an artifact or a misinterpretation, your career is damaged. You become the person who cried alien. Professional reputation matters in science. So you sit on the data. You show it to trusted colleagues. You request follow-up observations from other telescopes. You wait for confirmation. And while you're waiting, the data isn't public. This is human nature. It's not malicious. It's self-preservation, interagency politics. Space science is international. Multiple agencies, observatories, and institutions are tracking 3I Atlas, NASA, ESA, JAXA, individual university groups. If one of them has extraordinary data, there might be negotiations about how and when to release it, who gets credit, whose press release goes first, what the messaging should be. These negotiations take time. They can delay public disclosure. Even when there's no intent to suppress information permanently, bureaucracy and coordination are slow. Now, the Japanese origin claim for the leaked image. If that's true, the clip really did come from a Japanese source. What would that source look like? JAXA operates space missions, but none currently. Positioned to observe 3I Atlas at high resolution during perihelion, Japan's national observatories have ground-based telescopes capable of solar and near-solar observations. The Hida Observatory, for example, operates solar telescopes. University networks have smaller instruments. Any of these could theoretically have captured something, but if they didn't, if it were significant, you'd expect an official announcement. The absence of one suggests either the clip didn't come from an official source, or the source doesn't want to be identified. What would a real leak look like? In professional astronomy, data is stored in FITS format flexible image transport system. It's a standardized file format that includes not just the image, but also extensive metadata. Every FITS file has a header that tells you the telescope, the instrument, the filter, the exposure time, the observation date and time down to the second, the right ascension and declination of the pointing center, the detector temperature, the gain settings, the observer's name, the program ID. It's a forensic goldmine. If someone leaked a FITS file, astronomers could verify its authenticity within hours. They'd check whether the star field matches the claimed coordinates. They'd verify the point spread function against the known optical characteristics of that telescope. They'd check whether weather records from that night support the seeing conditions implied by the image quality. A real leak would be verifiable. What we have instead is a processed video clip with a watermark. No FITS header, no metadata. No way to trace it back to a specific instrument or observation. That's suspicious. It's consistent with either a hoax where someone created the clip and added a fake watermark to give it credibility, or a deliberately sanitized leak where someone stripped the metadata to protect the source. Both scenarios are possible. Neither can be ruled out. Commercial satellite data is another angle. Private companies operate Earth observation satellites with high-resolution cameras. Some of those satellites could theoretically be pointed at solar-adjacent targets if the geometry allows and the customer requests it. Commercial imagery doesn't go through the same public release pipelines as academic data. If a private entity captured something unusual, they might sit on it for business reasons, strategic reasons, or contractual obligations. This creates a data gap. Non-traditional sources producing observations that never enter the public domain. It complicates provenance and makes verification harder. There's also the possibility of intelligence assets. Military and intelligence satellites have capabilities that exceed publicly known civilian instruments. They're designed for Earth observation, but some have the flexibility to point at other targets. If such an asset captured 3I Atlas, a perihelion, that data would be classified. It wouldn't be released through scientific channels. It might not be released at all. And if it leaked, it would leak through intelligence communities, not astronomy forums. The watermark, the anonymity, the lack of metadata, all of that is more consistent with an intelligence leak than a scientific one. But here's the thing. Even if data is being withheld, even if there's a short-term holdback for quality control or interagency coordination or national security review, that doesn't automatically imply aliens. Institutions delay information release for all sorts of reasons. Part 9. Natural object counters and what would falsify craft hypothesists build the case for 3I Atlas as a natural object. Let's see how far we can get before the data forces us to admit we don't know. Start with the chemistry. Multiple spectroscopic observations have confirmed the presence of cyanide and atomic nickel in the coma. Cyanide is normal. It's one of the most common molecules detected in comets. It forms from carbon and nitrogen in the cold molecular clouds where comets are born. When a comet approaches the sun, solar ultraviolet light breaks apart larger molecules, liberating cyanide into the coma where it fluoresces and becomes detectable. Nothing strange about that. Nickel is less common, but not unprecedented. Several comets have shown metal emissions: calcium, sodium, iron, nickel. These metals are present in the rocky and metallic grains embedded in the comet's ice. When the ice sublimates, it exposes these grains to sunlight. The grains heat up. At high enough temperatures, the metals vaporize, releasing atoms into the comet. Those atoms absorb sunlight and re-emit it at characteristic wavelengths, creating emission lines that spectrographs can detect. The puzzle is why nickel is prominent but iron is weak or absent. In typical rocky material, iron is more abundant than nickel. The Sun's composition reflects the overall composition of the solar nebula, and in the Sun, iron outnumbers nickel by about 20-1. If 3I Atlas was simply vaporizing generic Raki grains, you'd expect strong iron lines and weaker nickel lines. Instead, you see the opposite. That's the anomaly. The carbonyl chemistry explanation is elegant. Under certain conditions, nickel reacts with carbon monoxide to form nickel tetracarbonyl. This is a well-known compound in industrial chemistry. It's a gas at room temperature, highly toxic and thermally unstable. When heated or exposed to ultraviolet light, it decomposes, releasing nickel atoms and carbon monoxide. The key is that nickel forms this carbonyl compound much more readily than iron does under cometary conditions. If the temperature and pressure in the comet's near surface layers fall within a specific range, nickel carbonyl can form and then photodissociate, pumping nickel atoms into the coma without a corresponding increase in iron. This process can explain the nickel-ovarian ratio naturally. Several peer-reviewed papers on 3I Atlas have discussed this mechanism. They've modeled the thermal and chemical environment near the nucleus and shown that carbonyl chemistry is plausible. It requires a carbon monoxide-rich environment, which JWST observations suggest is the case. 3I Atlas is CO2 rich and water poor at large heliocentric distances. That's unusual for solar system comets, but not impossible for an interstellar object formed in a different stellar environment. The chemistry, while strange, has a natural pathway. The sunward antitell has a proposed thermodynamic explanation. As well, when the sun-facing hemisphere of a comet heats up, it sublimates volatiles preferentially from that side. If the sublimation is vigorous enough, it creates a jet of gas and dust flowing away from the surface. If that jet happens to be oriented along the sun-comet line pointing sunward, it creates a feature that looks like an anti-tail. The jet isn't actually traveling toward the sun, it's traveling away from the nucleus. But because the nucleus is between the Sun and the observer. The jet appears to extend sunward. It's a geometry effect combined with active outgassing. This has been observed in other comets. It's rare, but it's natural. The water fraction is another point of difference. JWST detected low water abundance compared to typical solar system comets. But again, interstellar comets might form in environments where water ice is less abundant. Different temperature profiles in different protoplanetary disks lead to different volatile inventories. A comet formed in a system where carbon dioxide or carbon monoxide dominated over water ice would naturally have a low water fraction. It's not standard, but it's within the range of astrophysical possibilities. Diversity is expected in a galaxy full of planetary systems with different formation histories. Now the dynamics. The ultimate test of the craft hypothesis is the trajectory. If 3I Atlas's post-perihelion orbit matches the gravitonian predictions, that's strong evidence it's a natural object. Non-gravitational forces from outgassing can produce small deviations, but those deviations are typically random and small. In magnitude, if the observed trajectory after perihelion stays within the uncertainty envelope of the gravitational model, there's no need to invoke propulsion. The object is following Newton's laws. It's a comet. Outgassing torques can change a comet's rotation state and induce small orbital perturbations. This is well documented. When gas jets erupt from the surface, they exert a force on the nucleus. If the jets are asymmetric, the force creates a torque that changes the spin. If the jets have a net component along or against the direction of travel, they change the orbit. These effects are small but measurable. Astronomers modeled them by tracking the comet over time and fitting a force model that includes both gravity and non-gravitational accelerations. For 3I Atlas, if the non-gravitational acceleration is consistent in magnitude and direction with cometary outgassing, the natural explanation holds. Photometry is another test. If the alleged lights are real, they should behave like physical features attached to the object. They should rotate with the nucleus. They should maintain consistent brightness and color. They should show up in multiple filters. If instead they behave like point spread function artifacts, if they track with the seeing conditions and change from exposure to exposure in ways that don't correlate with the object's rotation, argues for instrumental effects. High cadence photometry over multiple nights can distinguish these cases. It's a falsifiable test. Though the data shows artifact behavior, the lights aren't real. If the data shows rotation-correlated behavior, they're real. And then the question becomes what they are. Thermal physics offers another natural mechanism for the bright leading edge. Small dust particles scatter sunlight efficiently in the forward direction. If 3I Atlas has a dust coma concentrated on the sunward side, and if the particle sizes and viewing geometry are right, forward scattering can make that side appear much brighter than the rest of the coma. This is phase angle dependent. The brightness should change as the phase angle changes. If observers track the object through different phase angles and see the predicted brightness variations, that supports the scattering explanation. If the brightness stays constant regardless of phase angle, that argues against scattering and for intrinsic emission. History is full of comets that looked strange. Comet LINEA are fragmented in 2000, producing a train of debris that looked structured and geometric in some images. Comet Ison disintegrated at perihelion in 2013, creating a knife-edge dust feature that appeared artificially sharp. Comet Shoemaker Levy 9 broke into fragments that looked like a string of pearls before impacting Jupiter in 1994. In each case, the unusual appearance had a natural explanation: fragmentation, tidal forces, differential sublimation, dust dynamics. Nature can produce shapes and structures that look engineered if you don't understand the underlying physics. The burden is on us to distinguish engineered from merely unusual. The burden of proof for the craft hypothesis is high. You'd need to demonstrate non-gravitational acceleration that can't be explained by out. You'd need resolved structure in multiple independent images that show symmetry and regularity inconsistent with natural processes. You'd need spectroscopic signatures that don't match known cometary chemistry. Ideally, you'd want emission at frequencies consistent with technological sources, radio carriers, laser lines, microwave beams, something unambiguous. None of that has been reported officially. All we have is morphology and timing, which are suggestive but not conclusive. What would change the skeptic's mind? A documented delta-V change in velocity that's larger than outgassing can produce, and points in a direction consistent with deliberate maneuvering. If 3I Atlas emerges from perihelion on a trajectory that shows a systematic deviation, change in orbital energy or angular momentum that requires forces outgassing can't provide that evidence. If the deviation is in the direction you'd expect from an Oberth burn, either accelerating out or decelerating into a bound orbit, that's stronger evidence. If multiple independent observers confirm the deviation and can't explain it with natural mechanisms, you're approaching proof. Resolved structure from multiple instruments would also be compelling. If Hubble, JWST, VLT, and Keck all capture images showing the same elongated, node-covered morphology, and if those images can't be explained by PSF artifacts or processing errors, you have to take it seriously. If the structure shows internal detail, there are features that look like joints, panels, antennas, emitters, things that have no business being on a comet, natural explanation collapses. Spectroscopy could be definitive. If someone detects emission lines that don't match any known cometary molecule or atomic transition, that's a red flag. If those lines are narrowband, indicating a non-thermal source, that's a bigger red flag. If the lines are or structured in ways that suggest information encoding, you're done. You've detected technology, but we're not there. The spectroscopy so far shows C, N, and nickel, both of which have natural explanations. Part 10. If it's artificial ramifications, let's assume, just for the length of this section, that 3I Atlas is artificial. A probe, a spacecraft built by intelligences that are not human, launched from a star system that is not ours, sent here. For purposes we can only guess at. What does that mean for us? The best case scenario is that it's a reconnaissance missioner, robotic explorer, fully autonomous, conducting a survey of the solar system. It's collecting data, mapping the planets, measuring the sun's output, sampling the composition of asteroids and comets, checking for biosignatures on Earth, Mars, maybe Europa, or It's doing science, the same kind of science we're trying to do with our missions to other worlds. In this scenario, the probe is passive. It observes but doesn't interact. It's not here to make contact. It's here to gather information and report back, or maybe to add our system to a growing database of surveyed stars. This is the optimistic read. First contact as mutual curiosity. Civilizations exploring the galaxy and eventually finding each other, because we're all curious about what's out there. In this scenario, the solar Oberth maneuver makes sense as a mission design choice. You enter the system on a hyperbolic trajectory. Pass close to the inner planets to maximize observation time, then use the sun's gravity well to accelerate back out. Maybe you're heading to the next star on the list. Maybe you're returning to your origin with a memory bank full of data. Either way, you're using the most efficient propulsion strategy available to a spacecraft with finite fuel. You're being smart about it, economical. That's what we would do. That's what any rational spacefaring civilization would do. The implications of this scenario are profound but not immediately threatening. It means interstellar travel is possible. It means someone achieved it before we did. It means the galaxy is not empty. There are others out there building machines, exploring, learning. It means we're part of a larger community, even if we've never met. It changes the context of human existence. We're no longer unique. We're no longer alone. Our achievements, our struggles, our history, all of it happens in a universe where intelligence and technology are not singular to Earth. That's humbling. It's also exciting. It opens futures we've barely imagined. Trade, communication, shared knowledge, maybe even collaboration across the light years. The long conversation begins, but there are darker scenarios. Surveillance without benign intent. Intelligence, surveillance, reconnaissance, military terminology. If 3i Atlas is an ISAR platform, it's not here to say hello. It's here to assess, to measure our capabilities, our technology level, our resource extraction, our military assets, our vulnerabilities. This is the reconnaissance that precedes action, not the exploration that satisfies curiosity. In this scenario, the probe might be part of a larger network of many sensor systems throughout the galaxy to identify targets of interest. The data it collects could be used to decide whether our system is worth visiting in person, worth exploiting, worth avoiding, or worth neutralizing. The Dark Forest hypothesis, popularized by Liu Cixin's science fiction trilogy, suggests that the galaxy might be filled with civilizations that remain silent because revealing your presence is existentially dangerous. If resources are finite and civilizations compete, the safest strategy is to hide and to eliminate any rival before they become a threat. In this framework, a probe like 3i Atlas is a scout. It's mapping the forest, identifying locations of other civilizations, reporting back to a predator that stays hidden until it's ready to strike. This is the paranoid interpretation. It's game theoretic. It assumes hostile intent because cooperation is risky and aggression is rewarded. It's also deeply unsettling because it implies that being discovered is the worst thing that could happen to humanity. Then there's the infrastructure scenario. The probe isn't just observing, it's deploying, establishing a relay network for communication, dropping sensors into orbit around the Sun or the planets, seeding the system with surveillance, equipment, or even kinetic delivery platforms, small inert objects that can be activated later if needed. This is strategic positioning, setting up the board for future moves. In this scenario, the Oberth maneuver could be used to place secondary payloads into specific orbits. You do your burn at perihelion, but instead of leaving the system entirely, you shed velocity and insert into a park in orbit. Maybe a heliocentric orbit that keeps you far from Earth but gives you a long-term observation platform. Maybe a Trojan orbit at a Lagrange point where gravitational balance lets you loiter with minimal fuel costs. You're not leaving. You're staying, watching, waiting. The strategic logic of a solar Oberth maneuver is compelling for any of these scenarios. The Sun's gravity well is the biggest energy source in the neighborhood. If you want to reach the inner planets quickly, you fall toward the Sun and use the acceleration to whip yourself into the right trajectory. If you want to reach the outer system, same strategy, different exit angle. If you want to break into orbit, you retrograde burn at perihelion. The efficiency gain is enormous compared to burning in deep space. Any civilization with an understanding of orbital mechanics would use this technique. The fact that 3I Atlas's trajectory brings it to the optimal location for such a maneuver is why the speculation won't die. Detectability. Going forward depends on what instruments are watching and where they're positioned. Ground-based telescopes will recover 3I Atlas in early November as it emerges from solar conjunction. Observers will measure its position and brightness. Spectroscopy will continue. If there's any anomaly in the trajectory, any sign of post-perihelion acceleration or deceleration, it will show up in the astrometry. But detecting the transient event a short thruster burn during conjunct is much harder. You'd need space-based observatories with the right geometry and the right sensitivity. JWST could do it if pointed correctly, but JWST's observing schedule is planned months in advance. You can't just commandeer it for a comet watch. Hubble has some flexibility but limited field of view. Planetary orbiters around Mars or in the inner system might catch something if they're looking at the right time. But that's luck, not design. Policy implications are murky. If evidence mounts that 3I Atlas is artificial, who leads the response? NASA is the obvious US candidate, but this isn't just an American issue. The European Space Agency, JAXA, the Russian Space Agency, the Chinese Space Agency, all of them have stakes in solar system exploration. The United Nations has a committee on the peaceful uses of outer space COPUS that handles international space policy. There's also the SETI Protocols, a set of guidelines developed by the scientific community for how to respond if we detect extraterrestrial intelligence. Those protocols emphasize transparency, international coordination, and avoiding hasty reactions. But the protocols were written with radio signals in mind, not physical objects in our solar system. The situation is different. The timeline is compressed. There's no time for leisurely international summits. Decisions would have to be made quickly, and the risk of unilateral action, one nation deciding to do something without consulting others, is real. Public communication becomes critical. The history of ambiguous astronomical events shows that information vacuums fill with speculation and fear. The wow signal in 1977 was a strong, narrowband radio signal detected by the Big Ear telescope. It lasted 72 seconds and was never seen again. To this day, nobody knows what it was. In the absence of a clear explanation, theories multiplied. Aliens, Soviet satellites, comets, interstellar scintillation, terrestrial interference. Was a lack of follow-up data left the question open, and the ambiguity fueled decades of debate. If 3I Atlas remains ambiguous, if the post-perihelion data is inconclusive, the same thing will happen. Stories will circulate. Theories will harden into beliefs. The truth, whatever it is, will be obscured by noise. Technological signatures to watch for include narrowband radio emissions. If 3I Atlas is transmitting data back to its origin, or if it's communicating with other probes in the system, it might use radio frequencies. Those transmissions could be detectable with Earth-based radio telescopes if someone's looking. Non-thermal infrared emissions are another signature. Spacecraft generate heat. Propulsion systems, power systems, even electronics produce waste, heat that has to be radiated away. If 3I Atlas is active, it should glow in the infrared at wavelengths that don't match solar heating alone. Specular flashes are a third signature. If the object has reflective surface-ized solar panels, mirrors, polished metal, those surfaces can produce bright glints when they catch sunlight at the right angle. If those glints repeat with a period tied to the object's rotation, that's evidence of artificial structures. All of these signatures are testable. They require the right instruments and the right observation plans, but they're within reach. Civilization. Implications are existential. If we're not the only engineers in the galaxy, our place in the cosmic hierarchy shifts. We're no longer the pinnacle of intelligence. We're one among many, possibly one among millions. Part 11. Fusion breakthrough, mast upgrades 3D coils tame El Mizon. A different front entirely. Something remarkable happened in fusion research. The UK Atomic Energy Authority announced a world-first achievement at the mast upgrade facility. They successfully controlled edge-localized modes ELMs, using three-dimensional magnetic coils in a spherical tokamak geometry. If you're not steeped in fusion jargon, let me translate. They figured out how to stop a plasma instability that has been one of the biggest obstacles to practical fusion power. Fusion is the process that powers stars. You take light, atomic nuclei, usually isotopes of hydrogen, and you slam them together at such high speeds and temperatures that they overcome their electrostatic repulsion and fused into heavier nuclei. The process releases energy, a lot of energy. The sun does this continuously, fusing hydrogen into helium in its core. If we can replicate that process on Earth in a controlled way, we have access to nearly limitless, clean energy. No carbon emissions, no long-lived radioactive waste, just deuterium and tritium, both isotopes of hydrogen fusing to produce helium and neutrons. The neutrons carry kinetic energy, which we capture as heat, which we use to generate electricity. The problem is containment. To get nuclei to fuse, you have to heat them to tens of millions of degrees. At those temperatures, matter becomes plasma fourth state, where electrons are stripped from atoms and everything is ionized. Plasma doesn't touch walls. It melts anything it contacts. So you have to contain it with magnetic fields, shaping. the plasma into a donut and holding it in midair with precisely controlled magnets. This is what a tokamak does. It's a magnetic bottle for plasma. But plasmas are unstable. They twist, they buckle. They develop instabilities that grow and crash, dumping energy into the walls and potentially damaging the reactor. One of the worst instabilities is the edge localized mode, or ELM. ELMs are periodic bursts of energy that erupt from the edge of the plasma and strike the inner walls of the tokamak. Each burst is brief, but the cumulative damage over time can destroy the wall. Materials. This is a showstopper for commercial fusion. You can't build a reactor that tears itself apart after a few weeks of operation. You need to suppress ELMs, or at least mitigate their effects. MAST Upgrade did it. They used a set of three-dimensional COIL electromagnets arranged around the tokamak that create complex magnetic field patterns. These patterns disturb the plasma edge in a controlled way, preventing the conditions that lead to It's like adding ripples to a pond to prevent larger waves from forming. The technique worked. The ELMs were suppressed. The plasma stayed stable. This is the first time it's been achieved in a spherical tokamak, which is a compact, efficient geometry that's central to the UK's plans for a commercial fusion power plant called STEP. Why does this matter for our story? Because fusion is the kind of energy source an advanced spacefaring civilization would use. Chemical rockets are limited by the energy density of their fuel. Even nuclear fission has limits. But fusion, if you can master, it gives you access to energy densities that make interstellar travel plausible. A fusion-powered spacecraft could accelerate continuously, building up to a significant fraction of light speed over the course of years. It could generate the electricity needed to run life support systems, communications, sensors, and propulsion, all from a compact, self-contained power plant. If 3i Atlas is a fusion-powered probe, the thermal signatures and the energy budget would be consistent with what MAST Upgrade and similar experiments are demonstrating on Earth. We're proving the physics works. Someone else might have already turned it into engineering. The Times covered the announcement, emphasizing the significance for the UK's fusion program. The official UK AEA release goes into technical detail. The achievement is real. It's peer-reviewed, in the sense that the results will be published in physics journals. It's reproducible. It's a building block for the next generation of fusion reactors. STEP is planned for the 2030s and 2040s. It won't produce power tomorrow, but the trajectory is clear. Fusion is no longer a distant dream. It's an engineering challenge being systematically solved. Taming star stuff in a bottle. That's what fusion is. Capturing the process that makes stars shine and putting it in a machine small enough to fit in a building. The magnetic braids, the three-dimensional coils, they're like invisible hands shaping the plasma, keeping it from touching the walls, guiding it into stability. It's beautiful physics and brutal engineering. The temperatures, the magnetic fields, the precision required of it is at the edge of what humanity can currently achieve, and we're achieving it, which means someone else, somewhere else, with more time and more resources, might have achieved it long ago. Next, we need to talk about the universe itself, about dark energy. the mysterious force that's accelerating the expansion of space. Because new models suggest that dark energy might not have been constant throughout cosmic history. It might have spiked in the very early universe, changing structure, formation, and indirectly affecting the distribution of matter that eventually became stars, planets, and perhaps the civilizations that build probes like 3I Atlas. Part 12. Very early dark energy update. Cosmology is the study of the universe at the largest scales. How it began, how it evolved, where it's going. One of the biggest mysteries in cosmology is dark energy. Observations of distant supernova in the late 1990s revealed that the universe's expansion is accelerating. Galaxies are moving apart faster now than they were in the past. This shouldn't happen if gravity is the only force at play. Gravity pulls things together. It should slow the expansion, but instead, the expansion is speeding up. Something is pushing space apart. And we call that something dark energy. The leading model for dark energy is the cosmological constant, term Einstein added to his equations of general relativity and later called his greatest blunder. The cosmological constant represents a constant energy density filling all of space. It doesn't change over time. It doesn't dilute as the universe expands. It's just there, everywhere, always pushing space apart. This model fits most of the data, but it leaves questions unanswered. Why does the cosmological constant have the value it does? Why is it so small compared to what quantum field theory predicts? These are the cosmological constant problems, and they're unsolved. Recently, researchers at the University of North Carolina, including Alex Sabotka, have been exploring an alternative, very early dark energy, or VEED. The idea is that dark energy wasn't constant throughout cosmic history. Instead, it spiked in the first few weeks after the Big Bang, then diluted away as the universe expanded. During that brief period, the extra energy density affected how matter clumped together. It changed the growth rate of density fluctuations, the seeds that eventually became galaxies and clusters. After the spike ended, the universe continued evolving. But the imprint of that early dark energy remained in the distribution of matter. Sabotka's modeling shows that VEED doesn't solve the Hubble tension outright. The Hubble tension is the discrepancy between measurements of the universe's expansion rate made using different methods. Observations of the early universe, the cosmic microwave background, give one answer. Observations of the late universe using supernova and Chi-Fi variables give a different answer. The two don't match. Something is wrong either with our measurements or with our model of cosmology. VEED tweaks the model, but it doesn't fully resolve the tension. What it does affect is small-scale structure formation, the way matter clumps on scales smaller than galaxy clusters. This has implications for the abundance and distribution of galaxies, which indirectly affects the rate at which planetary systems form, which affects the rate at which intelligent life might emerge. If VEED is real, it means the universe had a different expansion history in its first moments. That changes the timeline for when the first stars formed, when the first heavy elements were synthesized, when the first planets could have habitable conditions. It shifts the window for life to appear. If advanced civilizations emerged earlier than we thought. If the universe was conducive to life, sooner that increases the probability that someone else is out there, older than us, more advanced, possibly exploring the galaxy while we're still figuring out fire. This is relevant to 3i Atlas because the context of our discovery matters. If interstellar visitors are common, if the galaxy is teeming with probes sent by civilizations that arose billions of years ago, then 3i Atlas is just one of many. If, on the other hand, intelligent life is rare and we're among the first, then 3i Atlas is an extraordinary anomaly. VI doesn't answer that question directly, but it influences the background probabilities. The modeling is complex. It involves solving equations that describe how density fluctuations evolve in an expanding universe with time-varying dark energy. You have to match predictions to multiple data sets. The cosmic microwave background, large-scale structure surveys, gravitational lensing. Each data set constrains the model differently. VEED passes some tests, but needs confirmation across others. New surveys like Euclid and the Rubin Observatory will provide higher precision data on small-scale structure, and that data will either support VEED or rule it out for the general audience. The takeaway is this: the universe might have behaved differently in its earliest moments than we currently think. That changes the conditions under which galaxies and stars and planets formed. It affects the timeline for life. And it reminds us that cosmology, the study of the universe's history and fate, is still an evolving science. We don't have all the answers. We're refining the model as new data comes in. And every refinement changes the context for questions like, are we alone? And how common are interstellar visitors? Part 13. Hubble Tension Mirror Star Distance Ladder to 3.7%. Astronomers at the Inter-University Center for Astronomy and Astrophysics have pushed precision in measuring the universe's expansion rate to 3.7% using Mira variable stars as distance indicators. Miras are pulsating red giants with predictable brightness variations that serve as cosmic yardsticks, independent of the Kiffe variable and supernova methods that have dominated distance measurements for decades. This matters because, when different measurement techniques agree, it suggests systematic errors are less likely. And the Hubble tension, the maddening discrepancy between early universe and late universe expansion rate measurements, might point to genuinely new physics rather than observational mistakes. Better cosmic distances mean better understanding of how matter distributes across space, which affects our estimates for how many planetary systems exist, which affects how we calculate the probability of other technological civilizations arising. If 3i Atlas is artificial, these calculations shift from theoretical exercises to urgent strategic assessments. The Mira study, co-authored with members of Adam Rees's team who've been leading the precision cosmology charge, adds another independent check to the cosmic distance ladder. It doesn't solve everything, but it tightens the constraints. And tighter constraints mean we're closer to understanding whether the universe's structure favors rare or common technological life. The Hubble tension isn't just an academic squabble. It's a potential window into new physics. If the early universe measurements from the cosmic microwave background and the late universe measurements from supernova, Kiffe, and now Miras truly disagree, it might mean our standard model of cosmology is incomplete. Maybe dark energy isn't constant. Maybe gravity works differently on cosmic scales. Maybe there are particles we haven't discovered that affect expansion. Each possibility reshapes our cosmic context. For 3I Atlas, this matters because the probability of interstellar visitors depends on how common civilizations are, which depends on how common planets are, which depends on how galaxies form, which depends on how the universe expands. It's a chain of dependencies that starts with fundamental physics. If we're getting the expansion rate wrong, we're getting everything downstream wrong too. The mirror result doesn't resolve the tension, but it strengthens one side of the argument, the late universe measurements, by adding an independent method that agrees with the others. That makes the early universe measurements look more anomalous, which makes new physics more likely. The technique itself is elegant. Mira variables are old. Red giant stars that pulsate with periods tied to their intrinsic brightness. Like Kif, their standard candle zoo measure their pulsation period. You know their true brightness. You compare to how bright they appear and you calculate distance. But Miras are brighter than Kifits, which means you can see them from farther away. And they're different types of stars with different evolutionary histories, which means systematic errors that affect Kifits might not affect Miras. When multiple independent methods converge on the same answer, confidence grows. The 3.7% precision is impressive. It's not as tight as the Kifit supernova method, which is around 1 to 2%, but it's getting there. And crucially, it's independent. The team used mirrors in galaxies that also have Chi-feed measurements, allowing them to cross-calibrate. Then they extended the method to more distant galaxies, where Kifids are too faint to see. The result is a distance ladder that reaches farther into the universe with built-in checks against bias. What does this mean for 3I Atlas? If the late universe measurements hold, it suggests the universe is expanding faster than the early universe. Data predicts that could mean dark energy has changed over time, connecting back to the Veed hypothesis. It could mean there's additional physics at play. Either way, it affects how we model galaxy formation, star formation, planet formation, and ultimately the emergence of technology. If the universe expands faster, structures might form differently. If dark energy varies, the timeline for life might shift. These are subtle effects, but over billions of years, they add up. The Mirror study also demonstrates the power of using multiple, independent approaches to measure the same thing. In science, convergence is evidence. Part 14. Surveys that changed the game. Euclid and Rubin. The European Space Agency's Euclid mission has begun delivering science data, demonstrating exquisite wide-field imaging and spectroscopy that can probe low-surface brightness features and map cosmic structure at unprecedented scales. Meanwhile, the Vera C. Rubin Observatory has delivered its first light images, each frame capturing an area equivalent to 45 full moons, with a camera so sensitive it could detect a candle flame. On the moon, Rubin's legacy survey of space and time will scan the entire visible sky every few nights for 10 years. Astronomers estimate it could detect between 0.9 and 1.9 interstellar objects per year. That's dozens over the mission lifetime, caught earlier in their approach, with far better tracking than the rushed observations of 1I, Oumuamua, 2I Borisov, and 3I Atlas. Earlier detection means longer baseline observations before perihelion, which means better chances to flag non-gravitational behavior before objects enter solar conjunction blackout windows. Automated machine learning pipelines will scan Rubin's data stream for anomalies, flagging anything that moves strangely or looks morphologically unusual. When the next interstellar visitor arrives, we won't be caught flat-footed. We'll have months of pre-perihelion data, multiple independent observatories confirming morphology and chemistry, and time to coordinate international observation campaigns. The leaked images and ambiguous data surrounding 3I Atlas might become historical. Curiosities artifacts of a time when our detection infrastructure wasn't ready for what the galaxy was sending us. Or they might be the first chapter in a longer story, one where we realize the visitors have always been here, passing through, and we've only just started to notice Euclid's contribution is different but complementary. While Rubin focuses on time domain astronomy, finding things that change or move, Euclid focuses on the static universe, mapping the distribution of galaxies and dark matter across cosmic history. Its wide-field imager and spectrometer will create a 3D map of the universe, measuring how structures have grown over billions of years. This data will tighten constraints on cosmological models, potentially resolving the Hubble tension or revealing new physics like very early dark energy. For our story, Euclid helps answer the background question: how common are the conditions that lead to life and technology? Rubin, on the other hand, is the game changer for detecting interstellar objects. Its combination of wide field, deep imaging, and rapid cadence is purpose-built for finding faint, fast-moving things. The survey strategy, observing each patch of sky frequently with different filters, means that even objects that don't look like typical comets will be flagged. Machine learning algorithms trained on known objects will learn to recognize the unusual. And because Rubin will release data to the world within 24 hours, the global community can jump on discoveries immediately. Imagine the scenario. Rubin detects an incoming object months before it reaches the inner solar system. Early data shows an unusual trajectory, maybe aligned with the ecliptic, maybe with a close planetary encounter. Automated alerts go out to observatories worldwide. Space telescopes adjust their schedules. Amateur astronomers with specialized equipment are notified. By the time the object reaches perihelion, we have a comprehensive dataset, higher resolution imagery from multiple instruments, spectroscopy across the electromagnetic spectrum, precise astrometry tracking its position, and maybe even radar data from Arecibo or its successors. If the object performs an Oberth maneuver during conjunction, we have spacecraft positioned to catch it. If it's artificial, we know early. If it's natural, we have unprecedented data on a weird comet. This is the future of interstellar object studies. The ambiguity that surrounded Oumuamua and Borisovand, now 3I Atlas, will largely disappear. We'll still have mysteries, but they'll be better defined. We'll have the data to distinguish between natural and artificial with higher confidence. We'll be able to apply the full force of scientific methodology without the time pressure and observational gaps that plague current discoveries. Rubin's first light images already demonstrate its capabilities. The resolution, the depth, the sheer scale of the data's a leap forward. Each image contains billions of objects, from nearby asteroids to distant galaxies. Sorting through that torrent requires AI, but the algorithms are ready. The computing infrastructure is in place. The data pipelines are tested. When the survey begins in earnest, it will transform our view of the dynamic universe. Euclid's first data release shows the same leap in its domain. The maps of galaxy distribution, the measurements of weak gravitational lensing, the spectroscopic redshifts, all of it will refine our cosmic context. When we know how structures form, how galaxies evolve, how dark matter and dark energy shape the universe, will better understand the probabilities that lead to civilizations like ours or unlike ours together. These surveys represent a new era in astronomy, one where big data, machine learning, and international collaboration combine to answer some of the biggest questions. For 3I Atlas, they come too late to resolve the current ambiguity. But for the next visitor, they'll ensure we're prepared. Whether that visitor turns out to be a weird comet or something else, we'll have the tools to study it properly. And if it is something else, we'll have the evidence to convince even the skeptics. The timing is poetic. As we grapple with the possibility that 3I Atlas is artificial, we're building the infrastructure that will make such debates obsolete. We're moving from a time of accidental discovery and rushed observation to a time of systematic search and comprehensive study. The galaxy is sending us messengers. Soon we'll be ready to receive them properly. Part 15. What to watch next? The critical days ahead in early November 2025. 3I Atlas will emerge from solar conjunction. Observers worldwide will point their telescopes at the predicted coordinates and measure where the object actually is. They'll compare the observed position to gravity-only predictions and calculate residuals. If those residuals are consistent with random cometary outgassing, the craft hypothesis weakens significantly. If they show systematic deviation, velocity change pointing in a specific direction with magnitude larger than outgassing, can explain the conversation shifts immediately. Spectroscopy will continue. JWST, Hubble, Keck, and VLT will capture chemical profiles, searching for emissions that don't fit natural models. Amateur astronomers like Tiago will continue solar telescope monitoring through November, documenting morphology changes and looking for the tail that should develop as the object moves away from perihelion. Space assets, including SOHO and Stereo, will process their conjunction period data, and those datasets, when released, might contain the only direct observations of 3I Atlas. During its closest solar approach, we'll watch for radio emissions, infrared anomalies, and specular flashes that repeat with the object's rotation period. Every observation is a test. Every data point either supports or challenges the natural comet model. NASA states unequivocally that there is no impact risk. 3I Atlas will not hit Earth. The trouble implied in this video's title is paradigm trouble. The trouble of confronting evidence that challenges our cosmic solitude. If the post-perihelion data shows nothing unusual, if 3I Atlas behaves exactly as a comet should, we'll add it to the catalog as a fascinating but natural interstellar visitor with unusual chemistry. If the data shows anomalies that can't be reconciled with natural processes, if the trajectory deviates or the morphology resolves into obvious artificial structures, humanity faces a decision point. Do we attempt communication? Do we passively monitor and gather more data? Do we convene international bodies to coordinate policy? The SETI protocols exist, but they weren't written for physical objects, already in our solar system on trajectories we can predict. We're in uncharted territory, flying blind through the conjunction window, waiting for the sun to move aside so we can see what happened while we weren't looking. This might be the moment when everything changes, when we learn we're not alone and never were. Or it might be another strange comet, one more mystery in a universe full of them, reminding us that nature is stranger than we imagine and stranger than we can imagine. Either way, the data will come. The observers are ready. The telescopes are pointed, and in a few weeks, we'll know more than we do right now. Until then, keep watching the sky. Because whatever 3i Atlas turns out to be, it won't be the last visitor. The galaxy is vast, the stars are many, and the space between them is no longer empty. We're listening now, we're watching, and eventually, one way or another, we'll get our answer. The critical observations will happen in phases. First, as 3i Atlas emerges from conjunction, ground-based observatories will scramble to get positional fixes. The early astrometry will be rough, but sufficient to detect large trajectory changes. Within days, we should know if the object's orbit matches predictions. If it does, that's strong evidence for natural behavior. If it doesn't, the debate will intensify dramatically. Net spectroscopy will resume. The chemistry data was already unusual, but post-perihelion observations might show changes. If the nickel or cyanide emissions vary in ways inconsistent with solar heating, that's another red flag. If new elements appear, especially ones that don't typically occur in comets, that would be extraordinary. Imaging will be crucial. As the object moves away from the sun's glare, telescopes will be able to capture higher resolution images. If the alleged nodes along the spine persist, if they show rotation consistent with the object's spin period, if they appear in multiple independent observations with different instruments, the artificial explanation gains traction. If they disappear or are revealed as processing artifacts, the natural explanation wins. Radio observations will ramp up. SETI facilities like the Allen Telescope Array and the Green Bank Telescope will point their dishes at 3i Atlas, searching for narrowband signals that might indicate artificial transmission. Even a non-detection is useful. It sets limits on how powerful any transmitter might be. Infrared observations will be key for detecting thermal signatures. If 3i Atlas is generating heat beyond what solar heating would produce, say, from propulsion systems or electronicus, that excess should show up in the infrared. Space-based observatories like JWST are particularly suited for this, as they can observe at wavelengths blocked by Earth's atmosphere. The timing of all these observations depends on when exactly 3i Atlas emerges from conjunction and how quickly it moves away from the sun's glare. Early November is the target window, but it could shift by days depending on the exact geometry. Observatories have flexible time reserved for this, but scheduling is tight. especially for space-based assets. Amateur astronomers will play a crucial role. With their distributed global network, they can provide continuous coverage as Earth rotates. They'll be watching for changes in brightness, morphology, and any unusual behavior. Their observations, while less precise than professional facilities, can capture transient phenomena that might be missed between scheduled observations with larger telescopes. The data analysis will happen in real time. As observations come in, astronomers will process them, compare to models, and share results. The scientific community will be watching closely, ready to pounce on any anomalies. The media will be watching too, ready to report any developments. The public will be watching, hungry for answers. In the best case, the data will be clear and unambiguous. Either 3I Atlas behaves exactly as a weird but natural comet should, or it does something so obviously artificial that even the most skeptical scientists are convinced. In the worst case, the data will remain ambiguous. Just enough weirdness to keep the debate alive, but not enough to resolve it either way. That would be frustrating, but it would also motivate us to do better next time. Whatever happens, the story of 3I Atlas has already changed how we think about interstellar objects. It's highlighted the gaps in our detection capabilities, the need for better coordination, and the importance of being prepared for the unexpected. As Rubin and Euclid come online, as fusion research advances, as our cosmological understanding deepens, we're building the knowledge and tools to handle whatever the universe sends our way. The next few weeks will be critical. The next few years will be transformative. And the next few decades. If 3I Atlas turns out to be artificial, they might be unlike anything humanity has ever experienced. Keep watching. Part 16. The human factor, how we process the unprecedented. Let's step back from the technical details for a moment and consider something equally important. How we, as humans, and as a scientific community, process something as potentially paradigm-shattering as 3I Atlas. Because the biggest challenge isn't just gathering data or building better telescopes, overcoming our own cognitive biases, institutional inertia, and the fundamental difficulty of accepting something that challenges everything we thought we knew about our place in the universe. The history of science is littered with examples of ideas that were initially rejected because they were too radical. When Galileo proposed that the Earth orbits the Sun, he was met with fierce opposition, not just from religious authorities, but from fellow scientists who couldn't accept that our planet wasn't the center of everything. When Huygens suggested continental drift, geologists laughed. The idea that continents could move across the Earth's surface seemed ridiculous until plate tectonics provided a mechanism. When Barry Marshall proposed that bacteria cause stomach ulcers, the medical establishment dismissed him for years until he drank a culture of H. pylori and proved his point by giving himself ulcers. In each case, the resistance wasn't just about evidence. It was about how the new idea fit or didn't fit with existing frameworks of understanding. It was about the social and institutional structures that maintained scientific consensus. It was about the very human tendency to protect what we know, rather than embrace what we don't. If 3I Atlas turns out to be artificial, we'll face the same pattern on a global scale. The initial reaction will be disbelief. Even with clear evidence, many scientists will look for alternative explanations. They'll propose exotic natural phenomena that mimic artificial signatures. They'll point to uncertainties in the data. They'll demand extraordinary evidence for the extraordinary claim, and they'll be right to do so. That's how science works. But the demand for certainty can become a barrier to acceptance when the evidence is inherently ambiguous. Then comes the phase of grudging acceptance. As more data comes in, as multiple independent observations converge, as alternative explanations are exhausted, some scientists will start acknowledging the possibility of artificial origin. They'll be cautious, framing their conclusions in probabilistic terms. They'll emphasize the uncertainties. They'll call for more research. The consensus will begin to shift, but slowly. The media will amplify and distort every development. Headlines will swing between alien probe confirmed and scientists debunk extraterrestrial claims. Each new study will be cherry-picked to support pre-existing narratives. The public will be caught between competing claims, unsure what to believe. Social media will accelerate the spread of misinformation and conspiracy theories. In the absence of clear, authoritative communication, information vacuums will fill with speculation. Institutional responses will be complicated. NASA and other space agencies will face pressure to take a position, but they'll also be constrained by political considerations. If the evidence isn't ironclad, they'll likely adopt cautious language, emphasizing the need for further study. International coordination will be challenging. Different countries may interpret the same data differently, based on their own scientific cultures and political contexts. The public reaction will vary widely. Some will embrace the news as confirmation of long-held beliefs about extraterrestrial life. Others will reject it as part of a conspiracy or hoax. Many will experience genuine existential anxiety, the realization that humanity isn't alone in the universe can be deeply unsettling. Religious institutions will grapple with theological implications. Philosophers will debate the meaning for human identity and purpose. All of this human processing will happen while the scientific work continues. Astronomers will keep gathering data, refining models, testing hypotheses. Engineers will start thinking about how we might respond or interact. Policymakers will consider the implications for security, diplomacy, and resource allocation. The story will unfold on multiple tracks, simultaneously: scientific, social, political, cultural. The key challenge will be maintaining scientific rigor while being open to revolutionary possibilities. It's a delicate balance. Skepticism is essential to science, but excessive skepticism can blind us to reality. Open-mindedness is necessary for progress, but uncritical acceptance can lead us down false paths. The ideal approach is proportional belief, adjusting our confidence based on the quality and quantity of evidence, while acknowledging uncertainties. For 3i Atlas specifically, this means evaluating each piece of data on its merits. The trajectory deviation, if it occurs, will be strong evidence because orbital mechanics is well understood and precisely calculable. The morphology, if it resolves into clearly artificial structures, will be compelling because we have good criteria for distinguishing natural from engineered shapes. The chemistry, if it shows elements or isotopes in impossible combinations will be persuasive because we understand nuclear processes well. The spectroscopy, it detects narrowband emissions or modulated signals, will be convincing because we know how natural and artificial sources differ, but each of these lines of evidence could also have natural explanations. That's why convergence matters. If multiple, independent methods all point to artificiality, the case becomes stronger. If they conflict, we need to understand why. The human tendency is to seize on the evidence that supports our preferred conclusion and dismiss the rest. The scientific approach is to weigh all evidence, even when it doesn't fit neatly. The coming weeks and months will test our collective ability to process the unprecedented, whatever 3I Atlas turns out to be. The story of how we respond will tell us as much about ourselves as about the object. It will reveal our strengths, our curiosity, our capacity for rigorous inquiry, our ability to build instruments that can probe the cosmos. It will also reveal our weaknesses or institutional constraints, our difficulty with uncertainty. The ideal outcome is that we rise to the challenge, that we approach the mystery with both scientific rigor and philosophical depth, that we remain open to all possibilities while demanding evidence, that we prepare ourselves for a universe that might be more complex and interesting than we imagined. The ideal outcome is that the story of 3I Atlas becomes a case study in how humanity can collectively process something truly paradigm-shattering. Whether we'll achieve that ideal remains to be seen, but the opportunity is here. The data is coming. The universe is offering us a lesson. Are we ready to learn? Part 17. The technological imperative why. This discovery drives innovation, regardless of whether 3I Atlas turns out to be natural or artificial. The intense scrutiny it's receiving is already driving technological innovation across multiple fields. When humanity faces a compelling mystery, we respond by building better tools to solve it. The story of 3I Atlas is accelerating developments in observational astronomy, data processing, propulsion systems, and even artificial intelligence advances that will benefit science and society long after this particular object has left our solar system. In observational astronomy, the demand for better imaging of 3I Atlas has highlighted gaps in our current capabilities. Ground-based telescopes struggle with solar conjunction and atmospheric distortion. Space-based telescopes have limited flexibility and scheduling constraints. The result is a renewed push for next-generation instruments that can overcome these limitations. Several concepts are gaining momentum. Solar coronagraphs with advanced star shades that can block the sun's glare more effectively. Adaptive optics systems that can correct for atmospheric turbulence in real time. And orbital observatories positioned at Lagrange points that can maintain continuous observation during conjunction. The Vera C. Rubin Observatory, already mentioned, is one response to this need. But beyond Rubin, astronomers are proposing dedicated interstellar object observatories, optimized specifically for detecting and characterizing objects like 3I Atlas. These would combine wide-field survey capabilities with rapid follow-up instruments, allowing them to both discover visitors and study them in detail. Some proposals include space-based versions that could observe from outside Earth's orbit, avoiding conjunction limitations entirely. Data processing is another area seeing rapid advancement. The volume of information coming from modern observatories is staggering. Rubin alone will generate 20 terabytes of data per night. Making sense of this requires sophisticated machine learning algorithms that can identify anomalies, classify objects, and flag interesting phenomena for human review. The AI systems being developed for 3I Atlas analysis will become standard tools for all astronomy, helping us find everything from distant supernova to potentially hazardous asteroids. The specific challenge of distinguishing natural from artificial objects is driving innovation in pattern recognition and anomaly detection. Researchers are training neural networks on both natural phenomena and human-made objects, teaching them to recognize the subtle signatures of artificiality. These systems learn to identify regularities, symmetries, and other characteristics that might indicate engineering rather than natural formation. As these AI tools become more sophisticated, they'll be applicable beyond astronomy to fields like medical imaging, materials, science, and quality control. Propulsion systems research is getting an indirect boost from the Oberth maneuver discussions. The realization that an advanced civilization might use solar gravity assists for efficient interstellar travel has renewed interest in developing our own capabilities along these lines. While we're not ready to build interstellar probes, the physics principles involved could improve our solar system exploration. NASA and other agencies are studying missions that could use similar techniques to reach the outer planets more efficiently, reducing travel time and fuel requirements. Fusion research, as discussed earlier, is benefiting from the connection to potential propulsion systems for interstellar travel. The idea that 3I Atlas might be fusion-powered adds urgency and public interest to projects like ITER and the UK's STEP program. This increased attention translates to more funding, more talent entering the field, and faster progress toward practical fusion energy. Even if 3I Atlas turns out to be natural, this acceleration in fusion research could have transformative effects on energy production and climate change mitigation. The search for technosignatures, evidence of technology rather than biology, is becoming more sophisticated. Traditionally, SETI has focused on radio signals, but the 3I Atlas scenario has expanded the toolkit to include optical signatures, thermal anomalies, and orbital characteristics. The Technosignature project at Penn State and similar initiatives are developing catalogs of potential artificial markers that future observations can look for. This systematic approach makes the search more rigorous and increases the chances of recognizing artificial evidence if we encounter it. International collaboration is strengthening as a result of the 3I Atlas mystery. No single country or institution has all the resources needed to study such an object comprehensively. The response has been a growing network of agreements and data-sharing protocols that allow astronomers worldwide to coordinate observations and combine results. This infrastructure will remain valuable for all astronomical research, creating a more integrated, global scientific community. Public engagement with science has surged around the 3I Atlas story. The combination of mystery, cutting-edge technology, and profound implications has captured public imagination in a way few astronomical phenomena have. This increased interest translates to more support for science funding, more students entering STEM fields, and more informed public discourse about science policy. The long-term impact of this engagement could be as significant as the scientific discoveries themselves. Ethical frameworks for potential contacts are being developed in response to the 3-eye atlas scenario. While the object shows no signs of communication, the possibility that it could be artificial has prompted renewed discussion about protocols for contact. Organizations like the SETI Permanent Committee are updating their guidelines to cover physical objects in our solar system, not just distant signals. These discussions involve not just scientists but ethicists, philosophers, policy experts, and even theologians, creating interdisciplinary approaches to complex questions. The economic implications are driving innovation in commercial space. Companies are recognizing the potential value of being able to intercept and study interstellar objects. Several startups are proposing missions specifically designed for this purpose: smart, agile spacecraft that could be launched quickly when a new visitor is detected. While these concepts are still in early stages, the investment and talent flowing into them could accelerate the development of more responsive space exploration capabilities. Education is being transformed as well. The 3-eye atlas story provides a compelling narrative for teaching everything from orbital mechanics to spectroscopy to the scientific method. Educational institutions are incorporating the mystery into curricula, using real-time developments to engage students in the process of science. This approach makes learning more dynamic and shows students how scientific knowledge actually develops through observation, analysis, debate, and revision. Perhaps most importantly, 3-eye atlas is inspiring a new generation to look at the sky with wonder and curiosity. Just as the Apollo missions inspired previous generations, the possibility of encountering something from beyond our solar system is capturing imaginations worldwide. This inspiration is the ultimate driver of innovation. It's what motivates people to pursue careers in science and engineering, to ask big questions, and to push the boundaries of what's possible. Whatever 3-eye atlas turns out to be, its legacy will be the technological and scientific progress it has cut. The tools we're building, the skills we're developing, the collaborations we're forming, these will endure long after the object has continued its journey into the cosmos. In this sense, 3-eye atlas is already a gift to humanity, pushing us to become better observers, better thinkers, and better stewards of our cosmic curiosity. Part 18. The philosophical dimension: rethinking humanity's cosmic context. Beyond the scientific data and technological implications, the first atlas forces us to confront profound philosophical questions that have been largely theoretical until now. What does it mean to be human if we're not alone? How does our understanding of consciousness, intelligence, and purpose change when we encounter something that might be the product of another mind? These aren't just abstract musings, they're essential considerations for how we process the potential reality of extraterrestrial intelligence. The Copernican principle has been a cornerstone of modern astronomy for centuries. It states that Earth doesn't occupy a privileged position in the universe. that we're not at the center of everything. We've extended this principle over time. Our sun isn't special. Our galaxy isn't unique. Perhaps even our chemistry isn't extraordinary. But there's one aspect where we've maintained a kind of exceptionalism. The belief that intelligence, particularly technological intelligence, is rare or unique to Earth. 3I Atlas challenges this final bastion of cosmic spetterlings. If 3I Atlas is artificial, it suggests that intelligence arises elsewhere in the universe, not just life, but minds capable of building things that travel between stars. This would be a philosophical earthquake, comparable to the realization that Earth isn't the center of the universe, or that humans share a common ancestry with all life on our planet. It would complete the Copernican revolution, removing the last vestiges of our cosmic exceptionalism. The implications for how we view consciousness are profound. We've long wondered whether consciousness is an emergent property of complex systems, a divine gift, or something else entirely. If intelligence has evolved independently elsewhere, it suggests that consciousness might be a fundamental feature of the universe, arising under the right conditions wherever complexity allows. This perspective aligns with what some philosophers call panpsychism, the idea that consciousness is a basic property of matter, not something that magically appears in certain brains. The question of purpose becomes more urgent too. Human history has been shaped by our search for meaning through religion, philosophy, art, and science. Much of this search has been inward-looking, seeking purpose within human experience. If we're not alone, if other intelligences exist with their own histories and purposes, it contextualizes our own search. It suggests that meaning-making might be a universal activity, not just a human preoccupation. It raises the possibility of a cosmic conversation about purpose that transcends individual species. Our understanding of time would shift dramatically. Human civilization spans a few thousand years of recorded history, a blink in cosmic terms. If 3I Atlas represents a civilization that's millions or billions of years older, it forces us to confront the vastness of deep time. What might intelligence become after such timescales? What values might persist? What goals might drive beings who have witnessed cosmic evolution unfold? These questions stretch our imaginations and challenge our anthropocentric perspectives. The ethical dimension becomes cosmic in scope. We've developed ethical systems primarily for dealing with other humans, and to some extent with other life on Earth. But what are our ethical obligations to an extraterrestrial intelligence? If 3I Atlas is a probe, does it have rights? If it's observing us, do we have a right to privacy? These questions might seem premature, but thinking through them now prepares us for potential future contact. They force us to clarify our values and extend our moral consideration. Beyond familiar boundaries, the relationship between science and religion would be tested. Many religious traditions have incorporated the possibility of extraterrestrial life into their cosmologies, but actual evidence of artificial intelligence from beyond Earth would create new theological challenges. Some might see it as confirmation of divine creativity, others as a challenge to human-centered spiritual narratives. The history of science-religion interactions suggests that most traditions would eventually adapt, but the process could be contentious and revealing. Our concept of progress would be redefined. Human civilization has followed a particular trajectory of technological and social development. If 3i Atlas represents an alternative path, it forces us to question whether our way is universal or contingent. Are there inevitable stages in the development of intelligence, or do different intelligences follow completely different courses? The answer would reshape how we think about our own future and what constitutes progress. The psychological impact on individuals shouldn't be underestimated. Knowing that we're not alone would be exhilarating for some, terrifying for others. It might alleviate the cosmic loneliness that has haunted human consciousness. Or it might introduce new anxieties about our place in the universe. Some people might find meaning in being part of a larger cosmic community, while others might feel diminished by the realization that we're not the pinnacle of creation. These psychological responses would shape how society processes the discovery. Art and culture would be transformed. Throughout human history, we've created art about ourselves, our world, and our gods. The possibility of actual extraterrestrial intelligence would open up entirely new artistic territory. How do we represent the truly alien? How do we create art that acknowledges our cosmic context without reducing the other to a projection of ourselves? The artistic response to 3i Atlas could be as significant as the scientific one. Political philosophy would need to expand beyond Earth-centric models. We've developed systems for governing nations, for international relations, even for global cooperation. But what political frameworks apply to our relationship with extraterrestrial intelligence? Do we need new forms of cosmic governance? How? Do our concepts of rights, responsibilities, and justice scale to a cosmic context? These questions aren't just theoretical. They're practical considerations for how we might organize ourselves as a species facing a larger universe. The search for meaning would continue, but in a new context. Humans have always looked to the stars and wondered about our place. If those stars hold actual intelligences, our wandering becomes more directed. We might seek to understand their values, their purposes, their conceptions of meaning. This could enrich our own search or complicate it, depending on what we find. Either way, the dialogue between human and extraterrestrial conceptions of meaning could be transformative. Perhaps most importantly, 3i Atlas reminds us of the power of not knowing. In a world that increasingly values certainty and definitive answers, the mystery surrounding this object represents something valuable. The opportunity to sit with uncertainty, to question our assumptions, to remain open to possibilities that challenge our worldview. This intellectual humility is essential for both scientific progress and philosophical wisdom. Whatever 3i Atlas turns out to be, it has already expanded our philosophical horizons. It has forced us to think bigger, to question deeper, to imagine beyond the boundaries of human experience. In this sense, it's already a philosophical gift, prompt to examine who we are and what we might become in a universe that might be more populated, more complex, and more meaningful than we previously imagined. Part 19. The Cultural Ripple Effect. How 3i Atlas transforms society beyond the laboratories and observatories. Beyond the philosophical debates and policy discussions, the story of 3i Atlas is creating ripples throughout global culture. These cultural shifts might be less immediately apparent than scientific discoveries, but they're equally significant in shaping how humanity processes the possibility of extraterrestrial intelligence. From entertainment to education, from economics to politics. The cultural impact of 3i Atlas is already transforming how we see ourselves and our place in the cosmos. In entertainment and media, 3i Atlas has sparked a renaissance of cosmic storytelling. Hollywood and streaming platforms are rushing to develop projects inspired by the mystery, but with a new level of scientific authenticity. Unlike the alien invasion narratives of the past, many of these new stories explore more nuanced scenarios, scientific teams racing to understand an enigmatic object, international collaborations grappling with paradigm-shifting discoveries, societies adapting to the knowledge that they're not alone. This shift from conflict to curiosity in our entertainment narratives reflects and reinforces a more sophisticated public understanding of what contact might actually look like. The music, the world has also felt the influence. Composers and musicians across genres are creating works inspired by 3i Atlas, from classical symphonies that captured the cosmic scale of the discovery to electronic pieces that incorporate actual astronomical data converted into sound. These artistic responses help process the emotional and philosophical dimensions of the discovery, making it accessible beyond the scientific community. Visual arts are experiencing a similar transformation. Galleries are featuring exhibitions of cosmic artworks that engage with the themes of interstellar travel, extraterrestrial intelligence, and humanity's place in the universe. Digital artists are creating stunning visualizations of what 3i Atlas might look like, blending scientific accuracy with artistic imagination. These images circulate widely on social media, shaping public perception and making the abstract concepts more concrete. Literature, always quick to respond to new ideas, has seen an explosion of 3i Atlas-inspired works. Science fiction authors are exploring scenarios that go beyond traditional first contact stories, examining how societies might realistically respond to ambiguous evidence of extraterrestrial intelligence. Literary fiction is using the discovery as a backdrop for exploring very human questions about meaning, connection, and purpose. Even poetry has found new inspiration in the cosmic themes. Raised by 3i Atlas, education at all levels is being transformed. Elementary school teachers are using the mystery to engage students in science, teaching basic astronomy through the exciting story of a real interstellar visitor. High school physics classes are calculating orbital mechanics. Using actual data from 3i Atlas, universities are creating interdisciplinary courses that bring together astronomy, philosophy, sociology, and art to examine the discovery from multiple angles. This educational ripple effect will produce a generation more comfortable with cosmic perspectives and more skilled at thinking across disciplinary boundaries. The economics of space exploration is shifting. Investors and entrepreneurs are paying new attention to the commercial possibilities of interstellar object research. Companies are forming around technologies developed to study 3i Atlas, from advanced imaging systems to AI-powered data analysis. Space tourism companies are incorporating the possibility of seeing such objects into their long-term planning. The economic ecosystem around space is expanding. driven in part by the public excitement generated by 3i Atlas. Politics and governance are feeling the impact too. The international cooperation required to study 3i Atlas has strengthened diplomatic ties between space agencies and created new channels for scientific collaboration. At the same time, the discovery has raised questions about planetary defense and security that are prompting policy discussions. Some governments are increasing funding for astronomical research, recognizing the strategic importance of being able to detect and characterize objects entering our solar system. Religious communities are engaging with the implications in diverse ways. Some are incorporating 3i Atlas into their theological discussions, seeing it as evidence of a creator's infinite creativity. Others are grappling with how to reconcile potential extraterrestrial intelligence with their doctrines. Many are finding that the discovery enriches rather than challenges their spiritual perspectives, opening new avenues for thinking about humanity's relationship to the cosmos. Social media has played a crucial role in democratizing the discovery. Unlike previous astronomical breakthroughs that were filtered through institutional channels, information about 3i Atlas spreads directly from scientists to the public, with real-time updates as new observations come in. This direct access has created a global community of engaged followers who discuss developments, share insights, and even contribute to the analysis in small ways. The conversation happening on platforms like X, Reddit, and specialized forums represents a new model of public engagement with science. Urban planning and architecture are experiencing subtle influences. The idea of potentially hosting or responding to extraterrestrial intelligence is inspiring some architects to think about how our built environment reflects our cosmic context. Buildings that incorporate astronomical alignments, public spaces designed for stargazing, and monuments that celebrate humanity's place in the universe are all becoming more common. These physical manifestations of our expanding perspective help integrate the cosmic into daily life. Food and lifestyle culture might seem unrelated, but even here we see effects. The concept of cosmic cuisine, dishes inspired by astronomical phenomena or created to be eaten in zero gravity, has gained popularity. Wellness practices are incorporating cosmic themes, from meditation sessions timed to celestial events to yoga poses named after constellations. These might seem superficial, but they represent a deeper cultural shift toward seeing ourselves as part of a larger cosmic story. Fashion and design have embraced the aesthetic of 3i Atlas. Clothing lines featuring prints based on astronomical images, jewelry incorporating actual meteorite material, and home decor inspired by the sleek, mysterious appearance of the object have all become popular. These consumer products might seem trivial, but they help normalize the idea of interstellar objects and integrate them into our visual culture. The language we use is evolving. New terms have entered the lexicon. Oberth window for the optimal. Time to perform a solar gravity assist. Technologignature for evidence of technology rather than biology. Cosmic humility for the recognition that we might not be special in the universe. These linguistic innovations reflect and enable new ways of thinking about our place in the cosmos. Perhaps most importantly, 3i Atlas is creating a shared global narrative that transcends national and cultural boundaries. In a world often divided by differences, the mystery of this object provides a common point of fascination that brings people together. The shared experience of watching, waiting, and wondering creates a sense of global community that's increasingly rare in our fragmented world. This cultural transformation is still in its early stages. As more data comes in, and as our understanding of 3I Atlas evolves, these ripples will continue to spread. The full cultural impact might not be clear for years or even decades. But what's already apparent is that 3I Atlas is changing how we see ourselves, not just scientifically, but culturally, socially, and personally. It's expanding our collective imagination and creating new possibilities for how humanity might relate to the larger cosmos. Part 20. The Cosmic Perspective. What 3I Atlas teaches us about ourselves and our future ours. We approach the conclusion of this exploration into the mystery of 3I Atlas. It's worth stepping back to consider the bigger picture. Whatever this object turns out to be, natural comet, artificial probe, or something else entirely, it has already taught us profound lessons about ourselves, our methods, and our place in the universe. These lessons will shape humanity's cosmic journey long after 3I Atlas has continued its path through our solar system. The first lesson is the power of systematic observation. The detection of 3I Atlas wasn't accidental. It was the result of dedicated survey telescopes like Atlas that systematically scanned the sky night after night. This approach reminds us that major discoveries often come not from sudden breakthroughs, but from patient, methodical work. As we build more comprehensive survey systems like the Rubin Observatory, we're increasing our chances of finding whatever else the universe might be sending our way. The lesson is clear. Keep watching, keep recording, keep analyzing. The cosmos reveals its secrets to those who pay consistent attention. The second lesson is the value of interdisciplinary thinking. Understanding 3I Atlas has required more than just astronomy. It has needed insights from physics, chemistry, engineering, computer science, philosophy, sociology, and more. The most productive discussions have happened when experts from different fields bring their perspectives to bear on the mystery. This suggests that as we face increasingly complex challenges both in understanding the universe and in managing our own planet, we'll need to break down disciplinary silos and embrace holistic approaches. The third lesson is about humility. In the face of uncertainty, the story of 3I Atlas has been a masterclass in how science should handle ambiguity. Rather than rushing to conclusions, researchers have carefully weighed evidence, acknowledged uncertainties, and remained open to multiple possibilities. This intellectual humility doesn't weaken science. It strengthens it by keeping us honest about what we know and what we don't. In a world that often demands certainty, the ability to sit with uncertainty or continuing to seek answers is a valuable skill both in science and in life. The fourth lesson is the importance of international collaboration. No single country or institution has been able to study 3I Atlas comprehensively on its own. The most significant progress has come when observatories worldwide have coordinated their efforts, shared data, and combined their resources. This model of global cooperation will be essential for addressing many of the challenges humanity faces, from climate change to future cosmic discoveries. 3I Atlas reminds us that we're all in this together, sharing the same planet and the same cosmic neighborhood. The fifth lesson is about preparation and flexibility. The debate over 3I Atlas has revealed gaps in our observational capabilities, particularly during solar conjunction when Earth-based telescopes are blind. These gaps have motivated new proposals for space-based observatories and more flexible scheduling systems. The lesson is that we need to build not just for what we expect to find, but for the unexpected. Our scientific infrastructure should be adaptable enough to respond quickly when something surprising appears. The sixth lesson is the public's crucial role in science. Amateur astronomers like Tiago have made valuable contributions to studying 3I Atlas. Public interest has driven funding and attention to astronomical research. Social media has democratized access to information and allowed diverse voices to join the conversation. This engagement between professional scientists and the public enriches both sides, gives scientists broader perspectives, and gives the public a deeper understanding of how science works. The lesson is that science isn't just for scientists. It's a human endeavor that benefits from widespread participation. The seventh lesson is about balancing skepticism and openness. The scientific community has rightly demanded extraordinary evidence for the extraordinary, claimed that 3I Atlas might be artificial. At the same time, many researchers have remained open to the possibility and have designed observations to test it. This balanced maintaining rigorous standards while being willing to consider radical ideas essential for progress. Too much skepticism closes us off to new possibilities. Too much openness leads us down false paths. Finding the right balance is an ongoing challenge that 3I Atlas has brought into sharp focus. The eighth lesson is about perspective. Whatever 3I Atlas is, it reminds us that the universe is bigger, older, and more complex than we often imagine. It invites us to zoom out from our daily concerns and consider our cosmic context. This cosmic perspective doesn't diminish our lives. It enriches them by connecting us to something vast and mysterious. In a world that can feel small and divided, remembering that we're part of a larger cosmic story can be both humbling and inspiring. That the ninth lesson is about preparation for the future. Whether 3I Atlas is artificial or not, the possibility that we might someday encounter extraterrestrial intelligence is real. The discussions, protocols, and frameworks developed in response to 3I Atlas will serve us well if and when that day comes. By thinking through these issues now, we're preparing ourselves scientifically, philosophically, and politically for whatever the universe might send our way next. The 10th lesson is perhaps the most profound. 3I Atlas teaches us about the power of mystery. In an age of instant information and easy answers, the enduring uncertainty surrounding this object has sparked curiosity, driven innovation, and brought people together in shared wonder. Mystery isn't just an absence of knowledge. It's an invitation to explore, to question, to imagine. The fact that there are still things in the universe we don't understand isn't a failure. It's an opportunity as we wait for the post-perihelion data that will help resolve the mystery of 3I Atlas. We're already seeing these lessons play out. New telescopes are being built, international collaborations are forming, public engagement is growing. Our understanding of the universe is expanding. Whatever the final verdict on 3i Atlas, humanity is already better for having engaged with the question, the cosmic perspective. The 3i Atlas offers is ultimately hopeful. It suggests that we live in a universe worth exploring, full of phenomena that challenge our understanding and spark our curiosity. It reminds us that there's always more to learn, always more to discover, always more to wonder at. In a world that can often feel mundane or predictable, the mystery of 3i Atlas reawakens our sense of cosmic possibility. Perhaps that's the greatest gift of this enigmatic visitor. It has reminded us to look up with wonder, to approach the unknown with both rigor and openness, to work together across boundaries and differences, and to never stop asking questions. These are the qualities that have driven human progress throughout history, and they're the qualities that will carry us into whatever future the cosmos holds. As 3i Atlas continues its journey beyond our sun, on whatever trajectory it follows, it leaves behind a transformed humanity, one that has looked into the cosmic mirror and seen not just an object from beyond, but a reflection of our own curiosity, our own capacity for wonder, and our own endless quest to understand. In that reflection, we find not answers, but better questions. And in the vastness of space, as in the depths of human inquiry, better questions are always more valuable than final answers. The story of 3i Atlas isn't over. The most exciting chapters may still be ahead, but whatever happens next, we can be grateful for this cosmic visitor that has expanded our horizons, challenged our assumptions, and reminded us that in the grand scheme of the universe, we're part of something magnificent, mysterious, and endlessly worth exploring. Keep watching. The sky, the universe is still speaking, and we're finally learning how to listen.